New York has built the most ambitious and over-engineered megaprojects the world has ever seen. From underground tunnel networks to gravity-defying towers, these projects push the limits of money and imagination. Today, we uncover New York's biggest megaprojects and the staggering scale of what it took to reshape one of the most iconic places on Earth. The construction of Hudson Yards, located on the west side of Manhattan, represents one of the most ambitious private real estate developments in the history of the United States. The site, once dominated by an active train yard known as the West Side Yard, posed a formidable engineering challenge due to the need to build over 20 rail tracks in constant operation. The project's realization required a complex orchestration of civil, structural, and mechanical systems in order to create a functional and stable platform that could support multiple high-rise structures while allowing uninterrupted train service beneath. The initial phase of construction centered around the creation of a massive platform, which involved installing approximately 300 caissons. These deep foundation elements, bored between existing rail lines and into the bedrock below, served as vertical supports for the deck that would eventually span the yard. Each caisson was constructed using a combination of drilled shafts reinforced with steel and filled with high-strength concrete, reaching depths of up to 100 feet. Due to the spatial constraints imposed by the active rail operations, each caisson had to be installed with extreme precision using specialized rigs positioned during coordinated windows when train traffic was paused or rerouted. Above the caissons, structural steel grillages and transfer girders were installed to distribute building loads across the uneven geometry of the train yard. These steel elements, many of which weighed in excess of 100 tons, were fabricated off-site and delivered during low-traffic hours to reduce disruptions. Erection of the steel frame platform was carried out using crawler cranes and gantry systems designed to maneuver around the tight constraints of the site. Temporary scaffolding, shoring towers, and falsework were used extensively to stabilize the platform sections during assembly. Once the platform structure was complete, a complex network of utility corridors, ventilation systems, and access points was integrated into the void space between the train tracks and the platform deck. This included active cooling systems designed to dissipate the heat generated by diesel locomotives, as well as fire suppression systems, emergency egress routes, and conduits for electrical and telecommunication lines. Special attention was paid to drainage and water management, as the deck needed to remain impermeable and resistant to both surface runoff and the thermal stresses caused by seasonal freeze-thaw cycles. Simultaneously, vertical construction began above the platform with the erection of high-rise towers featuring both steel and reinforced concrete superstructures. Tower cranes were mounted directly onto the platform and sometimes even cantilevered off the side to accommodate building footprints. For residential and commercial towers, high-strength concrete was pumped from staging areas outside the yard through a series of reinforced pipelines, ensuring consistent quality and flow rate. Core walls, which housed elevators, stairs, and utilities, were slip-formed in a continuous process to accelerate vertical progress and maintain alignment. Curtain wall systems consisting of glass and aluminum panels were fabricated off-site and installed using motorized hoists and mast climbers. These units were engineered to meet stringent performance criteria related to wind loads, thermal insulation, and sound attenuation due to the exposure of the site and its proximity to the Hudson River. The facade systems were also integrated with mechanical louvers and operable components to support the sustainable design targets set for the project. Mechanical, electrical, and plumbing installations were coordinated using building information modeling to avoid clashes and maximize available ceiling space. Centralized utility plants were constructed to serve multiple buildings with chilled water, steam, and power, using a combination of cogeneration and high-efficiency equipment. These plants were interconnected through a network of underground tunnels and risers, carefully designed to minimize energy loss and facilitate future maintenance access. Interior build-outs varied depending on occupancy type, but generally involved raised access floors, demountable partition systems, and state-of-the-art fire protection and life safety systems. For the retail podium, load-bearing transfer slabs were installed to accommodate large open floor plans and dynamic occupancy loads. This required the use of high-performance concrete with additives that enhanced pumpability and cured strength, particularly for spans exceeding 50 feet. Public realm elements, including the plaza and landscaping above the platform, were constructed using a layered assembly that included structural foam, drainage mats, root barriers, and engineered soil. These layers supported a diverse range of plantings, pedestrian pathways, and stormwater retention features. Custom-designed tree pits and planters were built into the deck slab, allowing mature trees to thrive despite limited soil depth and exposure to wind shear. Throughout the construction process, logistics were a primary concern, as the confined urban site required just-in-time delivery scheduling, off-site staging areas, and constant coordination with city agencies and transit authorities. Noise and vibration monitoring, environmental controls, and dust suppression systems were continuously deployed to minimize impacts on neighboring communities and infrastructure. The overall success of Hudson Yards was underpinned by an integrated project delivery model, which relied on collaboration among architects, engineers, contractors, and stakeholders from the earliest planning stages. This level of integration allowed for accelerated construction timelines, efficient risk mitigation, and optimized resource use, culminating in the completion of a new urban neighborhood that seamlessly integrates infrastructure, real estate, and public space atop an active rail yard. The construction of the East Side Access Project in New York City is one of the most complex and technically challenging transit undertakings in the history of the United States. Designed to connect the Long Island Railroad to a new terminal beneath Grand Central Terminal in Manhattan, this massive infrastructure project required the excavation of multiple tunnel systems, the construction of subterranean caverns, and the integration of entirely new rail systems within one of the most densely built environments in the world. Spanning decades of planning and construction, the project unfolded deep beneath the city's surface, demanding extraordinary precision and coordination across multiple engineering disciplines. At the core of the East Side Access Project was the tunneling phase, which involved the excavation of nearly 15 miles of new tunnels beneath Queens and Manhattan. This began with the deployment of tunnel boring machines, each weighing hundreds of tons and extending over 400 feet in length. These machines were launched from access points in Queens and advanced westward under the East River through soft ground and bedrock. To maintain stability in varying geological conditions, different TBM technologies were employed, including earth pressure balance and slurry shield methods. The TBM simultaneously excavated and installed precast concrete segmental liners, forming a continuous circular tunnel as they progressed. Each tunnel required continuous monitoring of ground movement, with real-time data collected from instruments embedded in the surrounding soil and rock. Ground stabilization techniques such as ground freezing and jet grouting were employed where necessary to prevent subsidence and protect adjacent infrastructure. Spoil material from the excavation was transported via conveyor belts and muck trains to designated removal sites, where it was processed and disposed of according to environmental regulations. Once the primary tunnels were completed, work shifted to the construction of the Manhattan Caverns, which would house the new terminal platforms and tracks. Located approximately 100 feet below street level, these caverns were excavated using the controlled drill and blast method. Each blast was carefully calculated to fracture rock without damaging existing subway lines and utilities above. The excavated spaces were then stabilized using rock bolts, shotcrete, and steel ribs, followed by waterproofing membranes and reinforced concrete linings. The new terminal complex beneath Grand Central was designed as a bi-level structure featuring 4 platforms and 8 tracks. The layout included numerous cross passages, ventilation shafts, and emergency egress corridors. Each level was constructed with reinforced concrete floor slabs supported by massive girders and columns, engineered to distribute loads uniformly across the cavern walls and foundations. Structural steel framing was used extensively in mezzanine and concourse areas to allow for open spaces and flexibility in architectural finishes. A major component of the East Side Access Project was the installation of a complex track and signal system. This involved laying continuously welded rail on concrete ties set in ballastless track beds, designed for durability and low maintenance. The track alignment required precision to meet curvature and grade requirements, particularly as the trains transitioned from tunnel approaches into the terminal. Overhead catenary systems were replaced by a third rail electrification system compatible with Long Island Railroad rolling stock, necessitating the integration of new power substations and switching equipment. Advanced signal and train control systems were installed, including communications-based train control to enhance capacity and safety. These systems required extensive cabling, signal houses, and testing to ensure interoperability with the existing rail network. Fiber optic communication networks were also laid throughout the tunnels and terminal areas to support operational control and real-time monitoring. Vertical transportation was another critical aspect, given the significant depth of the terminal. High-capacity escalators, some extending over 90 feet in length, were installed to move passengers efficiently between the mezzanine and platform levels. Additionally, multiple banks of high-speed elevators were constructed to provide accessibility and redundancy. Mechanical rooms housing air handling units, chillers, and backup power systems were strategically located throughout the terminal to support passenger comfort and operational resilience. In Queens, the Harold Interlocking, one of the busiest rail junctions in the country, had to be completely reconfigured to accommodate new track alignments for East Side access. This required the installation of new flyovers, viaducts, and switches, while maintaining uninterrupted train service for Amtrak and the Long Island Railroad. Work in this area was conducted in multiple phases, involving track outages scheduled years in advance and executed with military precision. New signal towers and interlockings were built to streamline train movements and improve operational flexibility. The LaGuardia Airport redevelopment project in New York City was an extensive modernization effort aimed at transforming one of the most outdated major airports in the United States into a state-of-the-art transportation hub. The redevelopment involved the complete demolition and reconstruction of Terminals B and C, the building of new roadways and taxiways, installation of modern baggage handling and screening systems, and the integration of advanced mechanical and electrical infrastructure, all executed while maintaining full airport operations. Spanning over 800 acres, the project required innovative construction techniques and phased implementation to address the logistical complexities of building in a fully operational airfield. Initial site preparation for the redevelopment began with extensive demolition work, including the removal of obsolete terminal structures, parking garages, and auxiliary buildings. This phase also involved extensive utility relocation, as critical services such as electrical power, natural gas, potable water, sewer lines, and telecommunications had to be rerouted to maintain service continuity. In addition, environmental remediation was carried out in accordance with regulatory standards, including soil testing and removal of any contaminated material. One of the most challenging engineering aspects of the project was the construction of the new Terminal B, while the old terminal remained operational. To achieve this, the new head house, which would serve as the central terminal building, was constructed in phases. A steel superstructure was erected on deep foundations comprised of driven piles reaching down to bedrock. The pile caps and grade beams formed a stable base for the vertical elements of the building. Structural steel framing was then installed, including long-span roof trusses to support the expansive check-in and baggage claim areas. The use of prefabricated components helped accelerate construction while reducing on-site labor intensity. A distinctive feature of the new terminal layout was the use of dual pedestrian bridges spanning active aircraft taxiways. These bridges connect the head house to two island concourses and are constructed of steel box girders and reinforced concrete decking. They were erected using balanced cantilever techniques with temporary supports and tensioning systems to maintain stability during installation. Each bridge was designed to maintain a clearance height sufficient for Group 3 aircraft to pass beneath, requiring precise survey and alignment coordination. Airside construction included the development of new aircraft aprons, gates, and taxi lanes. This required excavation and grading to achieve proper slope and drainage, followed by the installation of sub-base layers, geotextiles, and Portland cement concrete pavement. Aircraft-rated pavement thicknesses were designed based on expected load distribution from narrow-body and wide-body aircraft. Jet blast fences and visual guidance systems were integrated into the apron design to ensure safety during aircraft movement. On the land side, new roadways were constructed to streamline vehicular access to the terminals. These roads featured elevated and at-grade sections built using cast-in-place concrete and precast segments. Foundations for elevated roadways included drilled shafts and pile-supported abutments. Traffic was managed using temporary detours and signage, while new bridges and ramps were staged to avoid interfering with ongoing operations. Interior construction of the new terminals prioritized modularity and flexibility. Raised access floors allowed for the distribution of power and data cables, while mechanical systems were suspended in accessible ceiling plenums. HVAC systems used air handlers with variable air volume controls, connected to a central chiller plant for efficient cooling. Advanced fire suppression systems, including wet pipe sprinklers and clean agent suppression in sensitive areas, were coordinated through 3D modeling to avoid conflicts with structural and mechanical elements. The baggage handling system represented a critical logistical element, comprising miles of conveyor belts, automatic sorters, and explosive detection systems. These were installed in stages, with integration and testing conducted in tandem to ensure seamless operation. The entire system was monitored by a centralized control room equipped with diagnostic tools for system performance and fault detection. Electrical infrastructure included the installation of new substations, switchgear, and emergency backup generators. Redundancy was built into the power supply network to ensure uninterrupted service to terminal systems. Lighting throughout the terminal employed LED fixtures with daylight harvesting controls, while building management systems monitored energy consumption, air quality, and equipment status. Sustainability played a significant role in the design and construction process. The terminal buildings incorporated high-performance glazing, green roofs, and low-flow plumbing fixtures to reduce environmental impact. Stormwater management features included bioswales, underground detention basins, and oil water separators to treat runoff before discharge. The construction team adopted a design-build-delivery method to streamline coordination between contractors and designers, enabling faster decision-making and reducing change orders. Coordination was further enhanced through the use of building information modeling, which allowed multidisciplinary teams to resolve conflicts virtually before beginning physical work. Weekly progress reviews, safety audits, and schedule updates ensured that construction proceeded according to plan despite the dynamic nature of the airport environment. The Javitz Center expansion project in New York City was a transformative construction endeavor that significantly increased the capacity and functionality of the Jacob K. Javitz Convention Center, one of the largest such facilities in the northeastern United States. The expansion added more than 1 million square feet of space, including exhibit halls, meeting rooms, a rooftop pavilion, and a state-of-the-art truck marshaling facility. Executed on a constrained urban site adjacent to the Hudson River and operating rail lines, the project required a combination of advanced structural engineering, phased logistics, and sustainability-driven design. The initial phase of the project focused on extensive site preparation. This involved clearing the western portion of the existing property, relocating underground utilities, and driving piles for the building foundation. The ground conditions included fill material and soft soils, necessitating the use of deep foundation systems. Steel H-piles were driven to refusal into glacial till and bedrock to support the new superstructure. These piles were then capped with reinforced concrete pile caps interconnected by grade beams, forming a stable platform for vertical construction. The expansion superstructure was designed using a steel frame system, chosen for its strength-to-weight ratio and speed of erection. The main exhibition hall required long-span roof trusses capable of supporting overhead rigging loads for events while providing a column-free interior. These trusses were assembled on-site and lifted into place using crawler cranes with high lifting capacity. The structural steel frame included moment-resisting connections to resist lateral loads from wind and seismic forces, supplemented by braced frames where architectural design permitted. The exterior envelope of the building was constructed using a unitized curtain wall system featuring high-performance glass and aluminum framing. The glass panels were fabricated with low emissivity coatings and frit patterns to control solar gain and reduce glare within the exhibition spaces. The building envelope also incorporated insulated metal panels and rain screen cladding, supported by subgirts attached to the structural frame. A continuous air barrier and vapor retarder were integrated behind the facade to ensure thermal performance and prevent moisture intrusion. One of the central features of the expansion was the truck marshaling facility. which included 4 levels of enclosed, climate-controlled space designed to accommodate up to 200 trucks. This facility was constructed using post-tension concrete slabs supported by concrete columns and shear walls. The structural system was engineered to carry heavy live loads and included clear spans and high ceilings to facilitate truck maneuvering. A vehicle guidance system was installed to optimize truck flow and minimize idling times. Vertical transportation throughout the expanded center was provided by multiple banks of elevators and escalators. Freight elevators with oversized cabs and high load ratings were installed to move large exhibits and equipment between levels. Passenger elevators and escalators were placed in high-traffic areas to support efficient movement of attendees and staff. All systems were integrated into a building-wide control system for monitoring and maintenance. Mechanical, electrical, and plumbing systems were designed to meet the demands of large-scale events. Air handling units were placed on mechanical floors and connected to a network of ductwork, with variable air volume boxes to provide zoning control. Chilled water and heating hot water were supplied from a central energy plant using high-efficiency chillers, boilers, and heat exchangers. Building automation systems controlled temperature, humidity, and ventilation in real time. Electrical distribution included new switchgear, step-down transformers, and emergency power via diesel generators and uninterruptible power supplies. The expansion also included a rooftop pavilion and terrace which doubled as a green roof and outdoor event space. This area was built using lightweight structural systems to reduce loading on the roof deck and included pavers on pedestal supports, planting beds, and integrated lighting. Stormwater runoff from the roof was captured and stored in underground cisterns for non-potable reuse, such as irrigation and cooling tower makeup water. Photovoltaic panels were installed to contribute renewable energy and offset utility consumption. Interior construction of the exhibition and meeting spaces emphasized durability, flexibility, and acoustic performance. Raised floors were used in selected areas to allow for reconfigurable power and data connections. Operable partitions divided large meeting rooms into smaller breakout spaces, with acoustic insulation to minimize sound transfer. Finishes included terrazzo, carpet tile, and gypsum board with high recycled content, all selected to meet LEED certification criteria. A major component of the construction effort was the integration of the expansion with the existing Javitz Center. This required selective demolition of exterior walls and structural elements, followed by tie-ins to existing mechanical and life safety systems. Phased construction ensured that the existing facility remained operational throughout the project. Temporary partitions, rerouted utilities, and interim egress paths were deployed to maintain safety and functionality. The construction of One Vanderbilt, a super-tall skyscraper located adjacent to Grand Central Terminal in Midtown Manhattan, involved a highly complex sequence of engineering, structural, and logistical operations. Rising to a height of over 1,000 feet, One Vanderbilt integrates advanced construction techniques and urban transit improvements into a single vertical development, setting a new benchmark for commercial office towers in densely built environments. The project demanded meticulous planning and coordination, particularly given its proximity to historic structures, active transit infrastructure, and high pedestrian traffic zones. Site preparation began with the demolition of several pre-existing mid-rise buildings. This process involved asbestos abatement, structural dismantling, and foundation removal. Due to the tight urban footprint and adjacent properties, much of the demolition was carried out using high-reach excavators and hydraulic breakers rather than traditional implosion or large-scale mechanical demolition. Once the site was cleared, excavation commenced for the new foundations, which reached over 60 feet below grade to accommodate the tower's deep basement levels and the integration of a new transit hall connecting to Grand Central Terminal. Subsurface conditions required the use of slurry wall construction to provide lateral earth support during excavation. A perimeter slurry wall, composed of reinforced concrete panels formed within bentonite-supported trenches, was installed to retain surrounding soils and water. Tiebacks and internal bracing were employed to ensure wall stability as excavation advanced. Excavated material was removed using conveyor belts and dump trucks, with loads scheduled during off-peak hours to minimize traffic disruption. The foundation system consisted of a combination of spread footings and deep caissons drilled into bedrock. The caissons, some exceeding 6 feet in diameter, were constructed using large rotary drilling rigs and reinforced with steel cages before being filled with high-strength concrete. These elements were designed to transfer the enormous vertical loads from the tower into the Manhattan schist below. A thick matte foundation slab was poured over the caissons, utilizing thousands of cubic yards of concrete delivered in a continuous 24-hour operation. The superstructure of One Vanderbilt utilized a composite structural system combining a reinforced concrete core with structural steel framing. The core, which houses elevators, stairs, and mechanical risers, was constructed first using slip-form technology. This technique involved the continuous pouring of concrete into a moving formwork system, allowing rapid vertical advancement. The core served as the backbone of the building, providing torsional resistance and lateral stability. Around the core, structural steel beams and columns were erected to form the building's floor framing. High-strength bolted and welded connections linked the steel elements, while metal decking and concrete topping slabs formed the composite floor systems. The building's tapering profile and multiple setbacks required specially fabricated steel members and custom connection details. Each steel floor was erected using tower cranes positioned within the core, later climbed to upper levels as the building rose. To achieve the building's slender profile and withstand wind loads, One Vanderbilt incorporated tuned mass damping systems at its upper levels. These systems consist of massive weights suspended and supported by hydraulic or spring systems, which counteract building sway during high wind events. The structural engineers also designed a system of outrigger trusses and belt trusses that tied perimeter columns to the central core, distributing lateral forces more efficiently and enhancing overall rigidity. The curtain wall system featured unitized glass and aluminum panels that were pre-assembled and tested off-site for quality and performance. Each panel included insulated glazing units with solar control coatings, contributing to the building's energy efficiency. The panels were hoisted into place using monorail rigs and suction equipment mounted to floor slabs, with careful alignment to ensure thermal and air barrier continuity. Integrated ventilation louvers and operable windows provided occupant comfort and facilitated natural airflow. Mechanical systems for One Vanderbilt were designed for high performance and tenant flexibility. The building was served by multiple mechanical floors housing chillers, air handling units, and water pumps. The chilled water system used high-efficiency centrifugal chillers with variable frequency drives, connected to fan-powered terminal units distributed throughout tenant spaces. The vertical distribution of mechanical services was handled through stacked mechanical shafts integrated within the core. Electrical infrastructure included redundant feeders from the utility grid, emergency diesel generators, and automatic transfer switches to ensure uninterrupted service. Advanced building management systems controlled lighting, HVAC, and security systems with sensors deployed to monitor occupancy and optimize energy use. High-capacity risers for telecommunications, data, and security cabling were installed to accommodate diverse tenant requirements. Vertical transportation consisted of over 40 elevators divided into zoned banks, some of which utilized destination dispatch technology to minimize wait times and energy use. Express elevators connected lower floors to sky lobbies, while service elevators were designed with extra depth to handle large tenant equipment and furniture. At the base of the tower, a new transit concourse was constructed to improve access to Grand Central Terminal and the subway lines beneath it. This involved underpinning sections of the historic terminal structure and constructing new passages, escalators, and ticketing areas. Complex waterproofing systems, including bentonite mats and integral water stops, were installed to protect the subterranean spaces from groundwater intrusion. Public realm improvements included widened sidewalks, landscape plazas, and an open-air pedestrian corridor that created visual and physical connections to Grand Central Terminal. Paving, lighting, and street furniture were coordinated to enhance pedestrian circulation and safety. The redevelopment of Penn Station in New York City is a large-scale infrastructure and architectural initiative designed to transform one of the most heavily trafficked and functionally outdated transportation hubs in the United States into a modern, efficient, and passenger-focused facility. This multifaceted project involves the complete overhaul of existing station elements, integration of new transit connections, and the construction of Moynihan Train Hall as an extension of Penn Station's operational footprint. The redevelopment process unfolded across multiple phases, each requiring intense coordination between civil, structural, mechanical, and transportation engineering disciplines, all while maintaining continuous transit service for hundreds of thousands of daily commuters. The first critical step in the redevelopment was the structural conversion of the James A. Farley Post Office building into the new Moynihan Train Hall. This Beaux-Arts structure, located directly west of Penn Station, was originally constructed with massive granite walls and steel floor framing. Adapting this historic facility to serve as a modern rail terminal required surgical demolition of interior structural elements and the reinforcement of floor slabs and columns to accommodate new loading requirements. The most dramatic transformation occurred with the installation of a vaulted steel and glass skylight system over the former mail sorting room, now repurposed as the main concourse. This skylight was supported by new structural steel arches tied into the existing steel framing through moment-resisting connections. The entire installation had to be designed to accommodate differential settlement, thermal expansion, and seismic movement. Beneath the concourse, platforms and tracks serving Amtrak and Long Island Railroad were upgraded to meet modern standards. This involved improving vertical circulation with new escalators and elevators, reinforcing platform edges, upgrading lighting, signage, and wayfinding systems, and integrating accessibility features in compliance with the Americans with Disabilities Act. The mechanical ventilation systems serving the platforms were also expanded, including the installation of new fans, air shafts, and smoke evacuation ducts. The expansion of concourse areas continued under the streets and buildings adjacent to the existing Penn Station, where new subterranean pedestrian corridors were excavated using a combination of cut and cover and hand mining techniques. These corridors were lined with waterproof concrete and outfitted with finishes that matched the aesthetic of the new train hall. Special care was taken during excavation to protect nearby building foundations and subway infrastructure, employing instrumentation to monitor ground movement in real time. Within the original Penn Station footprint, structural retrofits were carried out to open up the low-ceilinged areas that had long hindered passenger flow and visibility. This included the removal of non-structural mezzanines and drop ceilings, the relocation of HVAC ductwork, and the replacement of outdated mechanical systems. Load-bearing columns were clad with fire-rated materials, and floors were refinished with terrazzo and stone tile to improve durability and appearance. Lighting systems were upgraded to high-efficiency LED arrays, integrated with motion sensors and daylight harvesting controls. A new entrance pavilion was constructed on 7th Avenue, creating a prominent street-level presence for the station. The pavilion consisted of a steel-framed structure with a glass facade supported by tensioned cable trusses. This open and transparent design brought natural light into the concourse and served as a visual counterpoint to the previously closed-off street frontage. Beneath the entrance, new circulation stairs, escalators, and elevators were installed to move passengers from street level to concourse and platform levels with minimal congestion. Mechanical, electrical, and plumbing systems throughout the redeveloped station were completely overhauled. Central utility plants were upgraded with high-efficiency chillers, boilers, and air handling units. These systems were connected to a distributed network of variable air volume boxes and demand-controlled ventilation points designed to adapt to occupancy loads in real time. Electrical distribution was modernized with new substations, transformers, and switchgear capable of supporting expanded digital signage, surveillance systems, and tenant loads. All systems were tied into a centralized building management system with touchscreen controls, alarms, and energy monitoring capabilities. The redevelopment also emphasized sustainability, with features such as green roofing, stormwater management systems, and low-impact construction materials. Green roofs were installed atop portions of the Moynihan Train Hall and the new entrance pavilion, supported by reinforced roof slabs and integrated drainage systems. Stormwater runoff was directed to underground detention tanks and treated before being discharged or reused for non-potable applications such as irrigation. During the course of construction, maintaining uninterrupted train service remained a top priority. Work was scheduled in off-peak hours and overnight shifts to limit disruptions. Temporary barriers, rerouted access paths, and detailed construction phasing plans allowed contractors to isolate active work zones from public areas. Safety was ensured through real-time coordination with Amtrak, Long Island Railroad, and New Jersey Transit, with flagging crews and communication protocols in place for track-level activities. Coordination with existing infrastructure was another critical component of the project. Penn Station interfaces with subway lines, path trains, and multiple street-level transportation systems. The redevelopment included improvements to subway entrances, ticketing areas, and passageways connecting the transit systems. Structural ties were established between the old and new facilities, with seismic joints and expansion joints incorporated to account for differential movement between the structures. The Hudson Tunnel project, part of the broader Gateway program, represents one of the most critical infrastructure efforts in the northeastern United States, designed to create a new two-track rail tunnel beneath the Hudson River connecting New Jersey to Manhattan. This massive undertaking involves constructing an entirely new tunnel system, rehabilitating the existing North River tunnels, and upgrading related infrastructure to enhance capacity, reliability, and resiliency for Amtrak and New Jersey Transit operations. Given the complexity of tunneling beneath a river in a densely urbanized corridor, the project requires advanced geotechnical planning, innovative construction methodologies, and rigorous logistical coordination. The construction of the new Hudson Tunnel begins with the establishment of tunnel portals on both the New Jersey and Manhattan sides. On the west side, in North Bergen, site preparation includes clearing a large staging area, relocating utilities, and driving deep foundations for the tunnel entrance structure. This involves the use of soldier piles and lagging systems to create excavation support for the open-cut sections of the tunnel approach. The excavation is conducted in phases, with groundwater control measures such as weld points and deep wells installed to stabilize the soil and lower the water table. On the Manhattan side, the tunnel emerges beneath Hudson Yards, requiring intricate coordination with existing foundations, utilities, and operational rail infrastructure. Access shafts and launch boxes are constructed using slurry wall and secant pile techniques to create watertight enclosures. These structures serve as both tunnel access points and critical infrastructure for ventilation and emergency egress. Dewatering systems and continuous monitoring are essential throughout the excavation process to prevent settlement or structural damage to nearby buildings. The main tunnel drive is carried out using pressurized face tunnel boring machines, or TBMs, specially designed to operate in mixed face conditions comprising soft soils, silts, and bedrock. Each TBM is equipped with a rotating cutter head, shield, and trailing support systems that handle spoil removal, segment installation, and auxiliary systems. The TBMs are launched from the New Jersey side, advancing eastward beneath the Palisades, the Hudson River, and into Manhattan. As the machines progress, they install precast concrete segments to form the tunnel lining. Each ring comprises several curved segments with waterproof gaskets bolted and grouted in place to create a continuous sealed tunnel shell. Spoil material generated by the TBMs is transported via conveyor belts or muck trains to the portal areas for removal and disposal. The tunnel boring process is carefully monitored using automated systems that track TBM position, face pressure, cutter wear, and ground movement. Data is relayed to control rooms where engineers can adjust parameters in real time to optimize performance and mitigate risks. Once the twin bores are completed, a range of secondary construction activities takes place inside the tunnels. This includes the installation of track bed systems, drainage lines, utility conduits, and concrete walkways. A concrete invert is poured to create a flat surface for ballastless track systems, typically slab track, which ensures high-speed stability and reduced maintenance. Third rail or overhead catenary supports are anchored to the tunnel lining, depending on the electrification method used. Signal cable trays, fiber optic communication lines, and fire detection systems are integrated along the tunnel interior. Mechanical and electrical systems include powerful ventilation fans housed in dedicated shafts, designed to maintain air quality during regular operations and to evacuate smoke in the event of fire. Emergency lighting, evacuation signage, and public address systems are installed throughout the tunnels, with cross passages between bores spaced at regular intervals to facilitate emergency egress and firefighting access. At each tunnel portal, substations and switchgear are constructed to supply power to trains and tunnel systems. These facilities include redundant transformers, switchboards, and backup power sources such as diesel generators and uninterruptible power supplies. The entire tunnel is connected to a centralized control system that monitors train movement, environmental conditions, and system performance in real time. Simultaneously with the construction of the new tunnel, the project involves the future rehabilitation of the existing North River tunnels, which suffered saltwater damage during Hurricane Sandy and continue to degrade. Once the new tunnel is operational, rail traffic will be rerouted through the new bores, allowing the old tunnels to be taken offline sequentially for full restoration. This process includes the removal of deteriorated track systems, replacement of corroded bench walls, structural repairs to the concrete liner, installation of modern waterproofing membranes, and upgrades to all mechanical and electrical systems. The Hudson Tunnel project also incorporates track realignments and yard reconfigurations on both sides of the river. In New Jersey, additional work includes the construction of approach structures and flyovers to integrate the new tunnel into existing Amtrak and NJ transit lines. In Manhattan, the connection involves carefully threading the new tracks into Penn Station's complex and congested rail throat. This necessitates new signal interlockings, turnout installations, and extensive coordination with other rail improvement projects in the area. Environmental mitigation measures are implemented throughout construction to protect water quality, air quality, and adjacent ecosystems. These include sediment control barriers, air filtration for construction sites, and noise suppression systems. Special consideration is given to minimizing disruption to local communities and existing transportation networks. The construction of the new Highmark Stadium in Orchard Park, New York, the future home of the Buffalo Bills, involves the development of a modern open-air sports facility designed to enhance fan experience, operational efficiency, and long-term durability in a region known for its severe winter conditions. This multi-year, multi-billion-dollar project is being built adjacent to the existing stadium, allowing uninterrupted use of the current facility during construction. The project requires extensive coordination of site development, structural engineering, vertical construction, mechanical systems, and logistics in order to deliver a stadium suited for National Football League operations and year-round community use. The site work began with extensive geotechnical surveys and soil borings to determine subsurface conditions. Given the clayey soils and shallow groundwater common in the region, the stadium's foundation system was designed to include deep foundations consisting primarily of driven steel piles and reinforced concrete drilled piers. These foundation elements extend to layers of dense till or weathered bedrock to ensure settlement control and resistance to frost heave, a key concern in the region's freeze-thaw cycles. Foundation work also included pile caps and grade beams, which tied together vertical loads from superstructure columns and distributed them into the subgrade. Following earthwork and foundation construction, the stadium's structural system began rising from the ground. The primary vertical and lateral force-resisting systems are composed of structural steel frames using wide flange beams, box columns, and truss members to accommodate large spans over seating bowls and concourse levels. Erection of steel components was carried out using crawler cranes, mobile tower cranes, and temporary bracing towers to stabilize elements until permanent connections were completed. Bolted connections predominated for speed and ease of assembly, with some welded joints required for moment-resisting frames in the main concourse and canopy structures. The stadium features a continuous seating bowl with multiple tiers, supported by cast-in-place concrete raker beams and precast concrete treads and risers. These structural components were manufactured off-site and trucked in for installation, using heavy-duty lifting equipment. Precast elements were aligned and shimmed into place, then grouted and anchored to ensure a rigid connection to the supporting steel or concrete framework. Vomitories, stairs, and circulation corridors were integrated into the bowl structure, incorporating slip-resistant coatings and embedded tactile strips for accessibility compliance. A prominent feature of the stadium is its canopy structure. which is designed to cover a significant portion of the spectator seating while remaining open at the field level. The canopy is supported by long-span cantilevered trusses projecting from the outer edge of the upper seating bowl. These trusses were fabricated in segments and lifted into position, then post-tensioned to reduce deflection and improve load transfer. The canopy cladding includes metal panel systems and translucent roofing materials to allow natural light penetration while providing shelter from rain and snow. Snow load considerations were a primary design constraint, requiring robust framing and drainage systems to prevent ice accumulation and structural overstress. Mechanical systems within the stadium include air handling units, hydronic heating systems, and ventilation equipment tailored to the open-air nature of the venue. Large mechanical rooms were installed beneath the seating bowl and in service cores, housing boilers, pumps, and fan systems. Given the region's cold climate, radiant heating systems were embedded into portions of the concourses and key field-level areas to prevent freezing and ensure operational continuity. The field itself incorporates a subgrade heating system to prevent turf freezing and ensure safe playing conditions during late season and playoff games. Electrical systems included high-capacity feeders, switchgear, and lighting panels distributed through electrical closets and conduits hidden within wall cavities and floor trenches. LED lighting systems were installed throughout the stadium, including field lighting, which was mounted on the canopy structure to provide even illumination with minimal glare. Emergency power systems, including diesel generators and battery-backed UPS systems, ensure continuity of life safety and broadcast operations during outages. The stadium's vertical circulation is supported by escalators, elevators, and wide staircases, designed to handle rapid ingress and egress of over 60,000 spectators. Vertical cores were constructed using reinforced concrete shear walls with embedded elevator guide rails and MEP chaseways. All passenger elevators were installed with regenerative drives and machine roomless technology to reduce energy use and maintenance demands. Within the stadium envelope, premium seating areas, suites, clubs, and press facilities were constructed using structural framing and high-end interior finishes. These spaces included raised access floors, custom millwork, acoustic ceiling systems, and advanced audiovisual integration for real-time data display and broadcast capabilities. Extensive mechanical zoning and separate air handling units were used to isolate VIP areas from general circulation zones. On the exterior, the stadium design incorporates architectural metal panels, stone veneer, and curtain wall glazing in key entry points. Exterior plazas and arrival zones were constructed with reinforced concrete pavement, pavers, and landscape features, including stormwater planters and snow melt systems embedded in walkways. Security measures such as bollards, surveillance systems, and controlled entry points were coordinated with structural and civil design. Logistics played a central role throughout the construction process. Given the tight construction schedule, materials were procured using just-in-time delivery methods with on-site laydown areas minimized through advanced planning. Winter construction required temporary enclosures, heated work areas, and cold weather concrete practices, including admixtures and thermal blankets. The construction of One Manhattan Square, a luxury residential skyscraper located on the Lower East Side of Manhattan, required a carefully orchestrated approach to high-rise construction on a waterfront site with challenging geotechnical conditions and limited staging space. Rising over 800 feet in height, the tower features a slender profile and houses hundreds of residential units above a multi-level podium. The project involved extensive subsurface work, a reinforced concrete structural system, curtain wall facade installation, and the integration of extensive mechanical, electrical, and plumbing systems, all within the constraints of a dense urban environment. The first phase of construction focused on site excavation and foundation work. Given the site's proximity to the East River, groundwater management and soil stabilization were critical. Deep excavation was necessary to reach suitable load-bearing strata and accommodate below-grade parking and service levels. A perimeter slurry wall system was constructed to support the excavation and act as a long-term waterproofing barrier. This involved trenching around the site's perimeter, supporting the trench walls with bentonite slurry, and placing reinforcement cages followed by trammy concrete pours to form continuous wall panels. Within the slurry wall enclosure, mass excavation was conducted down to the foundation level. Dewatering systems using well points and sump pumps controlled groundwater intrusion, and real-time monitoring ensured excavation stability. The building's foundation consisted of a thick, reinforced concrete mat slab, designed to distribute vertical loads across the footprint while resisting hydrostatic uplift pressure. The mat was poured in large segments using high-strength concrete with admixtures to enhance durability and control curing. Vertical construction proceeded with the erection of a cast-in-place reinforced concrete superstructure. The building's structural system was composed of a central concrete core housing elevators, stairs, and mechanical risers, surrounded by perimeter columns and shear walls. The core was constructed using a jump form system, allowing continuous vertical progress while floor slabs were cast around it using flying formwork and table forms. Each floor cycle averaged several days with rebar post-tensioning cables and mechanical sleeve penetrations installed prior to concrete placement. High-strength concrete mixes were used to achieve the design compressive strength required for slender tower stability. Lateral loads from wind and seismic activity were resisted primarily by the stiffness of the core and the interaction of shear walls distributed along the tower's footprint. To reduce construction time, climbing formwork systems and tower cranes were deployed to support material delivery and personnel movement as the building rose. The tower's facade system featured a unitized curtain wall assembly composed of aluminum frames and insulated glass panels with low emissivity coatings. Each panel was fabricated off-site, pre-glazed, and tested for air and water infiltration before delivery to the site. Curtain wall installation occurred concurrently with structural work, with panels hoisted into position and anchored to embedded inserts at slab edges. The panels also included spandrel sections to conceal floor slabs and mechanical systems, providing a continuous visual envelope. Mechanical, electrical, and plumbing systems were routed vertically through dedicated shafts within the core and extended horizontally across each floor plate. The building's HVAC system relied on fan coil units and centralized chillers located in mechanical floors, supported by rooftop equipment and condenser water loops. Fresh air intake and exhaust systems were integrated into the facade using hidden louvers and custom architectural details. Plumbing systems were zoned by floor and included pressure-boosting pumps and backflow prevention devices to maintain consistent service across all levels. Electrical systems included dual utility feeds, on-site transformers, and emergency backup generators. Sub-metering was implemented to track usage by individual residential units, and distribution panels were installed in closets on each floor. Fire protection systems consisted of wet pipe sprinkler systems, standpipes, and fire alarm wiring, all coordinated using building information modeling to avoid conflicts with structure and finish systems. Interior fit-out began once the building envelope was enclosed and permanent power was established. Each residential unit featured gypsum board partitions, sound-rated floor assemblies, and high-end finishes including wood flooring, custom cabinetry, and stone countertops. Kitchens and bathrooms were prefabricated as modular assemblies where possible to accelerate installation and improve quality control. Energy-efficient appliances, LED lighting, and smart home technology were integrated into the units. Amenity spaces were constructed within the building's podium and included fitness areas, lounges, spa facilities, and entertainment rooms. These spaces required specialized mechanical zoning and sound isolation to provide acoustic comfort and performance. Finishes in these areas included acoustic ceilings, soft flooring, and decorative lighting systems. An exterior landscape terrace was built over the podium roof slab, incorporating lightweight fill, waterproofing membranes, and stormwater management features such as planters and drainage mats. Vertical transportation systems included high-speed elevators equipped with destination dispatch technology to reduce wait times and improve traffic flow. Elevator shafts were constructed using slip-form techniques within the core, and guide rails, cabs, and control systems were installed once the structure topped out. Life safety systems were interconnected through a central command center, with emergency lighting, public address systems, and integrated surveillance and access control equipment. Throughout construction, logistics were tightly controlled due to the site's urban setting. Deliveries were scheduled in narrow windows, materials were staged just in time, and vertical hoists and cranes were used to reduce on-site clutter. Coordination with city agencies ensured that street closures, utility connections, and construction access points were managed without disrupting surrounding traffic and pedestrian activity. The Bronx Point development is a transformative mixed-use project situated along the Harlem River waterfront in the South Bronx. Designed to anchor the revitalization of the Lower Concourse neighborhood, this project blends residential housing, public open space, cultural institutions, and retail infrastructure into a cohesive, community-oriented development. The construction of Bronx Point required a multifaceted engineering approach to address floodplain conditions, brownfield remediation, vertical building systems, and public realm integration on a complex site once used for industrial and municipal purposes. Site preparation began with environmental remediation, as the location was designated a brownfield due to prior industrial use. This involved soil excavation, off-site disposal of contaminated material, and capping of subgrade layers with engineered fill. To stabilize the site for vertical construction, deep foundations were required due to weak soils and the site's location in a designated flood zone. Pile driving commenced using steel H-piles and mini-caissons, reaching down to competent load-bearing strata. Pile caps and grade beams were poured to support the superstructure and resist hydrostatic pressure. Given the site's flood-prone nature, the ground floor of the development was elevated above the base flood elevation, with waterproofing systems integrated into the foundation and slab edges. Passive flood protection measures included concrete knee walls, deployable floodgates, and sealed utility penetrations. Drainage systems with check valves and stormwater retention tanks were installed to manage runoff and reduce combined sewer overflow risk during extreme weather events. The residential portion of Bronx Point was constructed using a reinforced concrete frame. The structure consisted of shear walls and flat slab construction to maximize ceiling height and accommodate varied unit layouts. Formwork systems allowed rapid cycle times, with daily concrete placements coordinated alongside rebar and conduit installation. The tower was capped with mechanical bulkheads and roof-level amenities constructed using lightweight steel framing. The facade utilized a combination of brick masonry, metal panels, and punched window systems, referencing local architectural language while maintaining energy performance. Exterior insulation and air barrier systems were installed behind cladding to meet thermal efficiency requirements. Window systems incorporated low emissivity glass and thermally broken frames, enhancing insulation and reducing solar heat gain. Mechanical, electrical, and plumbing systems were zoned by core risers, with rooftop air handlers and energy recovery units providing ventilation and conditioning. High-efficiency condensing boilers supplied domestic hot water, while water-saving fixtures and submeters promoted conservation. Electrical infrastructure included LED lighting, solar-ready provisions, and smart metering. Fire protection systems included sprinkler and standpipe networks tied into a central fire command station. A major feature of the development was the inclusion of the Universal Hip Hop Museum, constructed within a large ground-floor volume. This space required long-span steel framing, acoustic isolation, and specialized MEP systems for exhibition climate control. Adjacent public plazas and waterfront esplanades were constructed with pile-supported decks, landscaping, and custom lighting. The entire site was knit together through resilient design principles, providing both community utility and urban resilience. Bronx Point stands as a model of integrated, equitable, and sustainable development in a historically underserved part of New York City. The American Legion Bridge Replacement Project is a critical infrastructure effort aimed at modernizing a key segment of the Capital Beltway, specifically the Interstate 495 corridor that spans the Potomac River between Maryland and Virginia. The existing American Legion Bridge, originally constructed in 1962, has long operated over capacity, experiencing severe congestion and structural fatigue due to increasing vehicular loads. The replacement project involves the complete removal of the aging bridge and construction of a new, expanded structure with improved capacity, safety, and multimodal functionality, all executed while maintaining active traffic flow across one of the busiest regional thoroughfares in the Mid-Atlantic. Construction begins with extensive preparatory work on both the Maryland and Virginia approaches. This includes widening the approach roads, relocating utilities, and constructing temporary service roads and retaining walls. Given the high traffic volume, much of this work occurs during off-peak hours with protective barriers and advanced traffic management systems deployed to safeguard workers and minimize disruptions. Intelligent transportation systems, including dynamic signage and real-time traffic monitoring, are established early in the project to maintain safe and efficient operations throughout construction. The new bridge is designed as a multi-span, pre-stressed concrete and steel girder structure with a substantially wider deck than its predecessor. It will accommodate additional general-purpose lanes, managed toll lanes in each direction, full shoulders, and a shared use path for pedestrians and cyclists. To support this expanded deck width, the new substructure includes larger piers and abutments constructed on deep foundations. Drilled shafts and driven steel piles are employed to reach load-bearing rock formations beneath the riverbed, with extensive underwater geotechnical investigations conducted to guide pile placement and sizing. Before the existing bridge can be removed, new bridge elements are constructed parallel to or in segments alongside the current bridge alignment. This phased construction approach minimizes the need for full closures, as traffic can be diverted to temporary bridge sections or shifted onto newly completed portions of the structure. Barges and temporary trestles are used to support materials transport and crane operations on the river, reducing dependency on land-based access and improving construction efficiency in the constrained corridor. The bridge superstructure consists of a composite steel girder and concrete deck system. Long-span steel girders are fabricated off-site, trucked to staging areas, and lifted into position using barge-mounted cranes and land-based crawler cranes. The girders are then spliced and secured using field welding and bolted connections. Once in place, the cast-in-place concrete deck is poured in sections, using form travelers and screeding equipment to ensure uniform thickness and surface smoothness. The deck is reinforced with high-strength steel rebar and includes post-tension tendons for enhanced performance under dynamic traffic loading. Drainage and expansion systems are integral to the bridge's durability. Deck drains, scuppers, and downspouts are installed to direct stormwater into collection systems without discharging directly into the river. Expansion joints and elastomeric bearings accommodate temperature-induced movements and vehicular loading, while corrosion-resistant materials and coatings are specified throughout to withstand de-icing chemicals and riverine humidity. The shared use path, located on the upstream side of the bridge, is physically separated from vehicular traffic and includes safety railings, lighting, and observation points. It connects to regional trail networks on both sides of the Potomac, enhancing non-motorized connectivity between Maryland and Virginia. The path structure is cantilevered from the main deck girders and supported with steel outriggers and braced frames designed for pedestrian loads and vibration criteria. Approach work involves realigning entrance and exit ramps, expanding merge lanes, and upgrading interchanges near the bridge termini. Retaining walls, noise barriers, and landscaping are constructed in tandem with grading and paving operations. Signal systems, gantries for toll lane management, and overhead variable message signs are installed and connected to regional traffic control centers via fiber optic networks embedded in conduit runs along the bridge structure. Environmental protections are implemented throughout the construction process. Silt curtains, turbidity barriers, and erosion control blankets prevent sediment from entering the Potomac River. Construction activities are scheduled to avoid sensitive spawning seasons for aquatic life, and work platforms are equipped with spill containment measures. The project also includes habitat restoration features such as riverbank stabilization and replanting of native vegetation along disturbed shoreline areas. Bridge lighting is designed to minimize glare and light pollution, using LED fixtures with shielded optics. Power and communication conduits are embedded in the deck to serve future upgrades in traffic technology and maintenance monitoring. The bridge is equipped with structural health monitoring sensors embedded in key components to collect data on strain, vibration, and temperature, allowing for predictive maintenance and long-term performance evaluation. Once traffic is fully shifted onto the new bridge, the original American Legion Bridge is dismantled in sections. This demolition process is executed using a combination of wire sawing, controlled explosive charges for superstructure removal, and mechanical dismantling. Steel girders and concrete components are removed by barge and processed off-site for recycling and reuse. Sound Transit 3, often abbreviated as ST3, is a massive, multi-decade transportation infrastructure expansion project in the Seattle metropolitan region. It builds upon the earlier SoundMove and ST2 initiatives by significantly enlarging the regional light rail, bus, rapid transit, and commuter rail systems. The centerpiece of ST3 is over 60 miles of new light rail lines, which are being developed through phased construction efforts extending into the 2040s. The construction process begins with corridor identification, environmental impact studies, and community consultations. Engineers perform geotechnical surveys using boreholes and core sampling to understand subsurface conditions. Once the alignments are finalized, utility relocation takes place. This involves rerouting water, gas, electric, and telecom lines that intersect proposed trackways and stations. Earthwork follows with excavation and grading for at-grade segments, and tunneling operations initiated for underground portions. For tunnels, tunnel boring machines are deployed, often starting from launch pits constructed at key portal locations. These machines advance slowly, installing precast concrete segmental linings as they progress. For elevated rail, large-diameter drilled shafts and pile foundations support cast-in-place or precast segmental bridge spans. These elevated guideways are assembled using cranes and form travelers, depending on span length and urban constraints. Simultaneously, construction of maintenance bases and operation control centers is undertaken. These facilities are critical for housing rolling stock and coordinating train operations. Station construction is another vital component, with excavation, foundation pours, steel erection, and architectural finishes being executed in sequence. Many of these stations are designed to integrate with bus transit, biking facilities, and pedestrian infrastructure. Track lane includes concrete plinth or ballast track construction, depending on whether the line is underground, elevated, or at grade. Overhead catenary systems are installed for electric traction alongside signal systems, communication cables, and substations for power distribution. ST3 also includes major upgrades to existing infrastructure, which involves service interruption planning, night shifts, and temporary track diversions. Every step is overseen with rigorous quality control, safety protocols, and coordination with municipal agencies to minimize public disruption. The Giga Texas expansion, taking place at Tesla's sprawling manufacturing campus near Austin, Texas, represents a significant scaling effort aimed at boosting production capacity across multiple vehicle lines, battery systems, and structural components. Originally developed as a massive integrated factory for Model Y and Cybertruck production, the expansion adds several million square feet of manufacturing space, auxiliary facilities, and infrastructure to accommodate increased throughput and new production technologies. Construction activities began with clearing and earthworks on adjacent parcels of land to the existing plant, involving extensive excavation, grading, and soil stabilization to create uniform building pads capable of supporting heavy industrial structures. To counter the region's expansive clay soils, foundation work employed deep-drilled piers and reinforced concrete mat slabs. In some areas, ground improvement measures such as lime stabilization and geotextile reinforcement were used to enhance load-bearing capacity and mitigate settlement risks. The structural steel framework for the new buildings was erected using high-capacity cranes and modular assembly techniques to expedite construction timelines. Prefabricated steel columns, beams, and joists were bolted and welded into place, forming large-span bays that allow for uninterrupted production floor layouts. Roof systems were installed using insulated metal panels or single-ply membrane systems, supported by lightweight purlins and designed to accommodate mechanical units, skylights, and solar arrays. Interior construction followed a just-in-time approach, with mechanical, electrical, and plumbing trades coordinating installations to align with equipment delivery schedules. High-voltage electrical rooms, compressed air systems, process cooling loops, and ventilation ducts were integrated alongside the structural envelope. Specialized utility trenches were installed throughout the production halls to support robotic assembly lines, material handling conveyors, and automated guided vehicle systems. Battery production areas were fitted with climate-controlled environments, explosion-proof fixtures, and dry rooms with dehumidification systems to meet strict environmental controls required for lithium-ion cell manufacturing. These spaces required isolated foundations and vibration-damping floor assemblies to support precision machinery for electrode coating, cell assembly, and electrolyte filling. Additional facilities constructed as part of the expansion include logistics hubs, employee amenities, research labs, and test tracks. Roadways, stormwater detention ponds, and utility corridors were extended to support the new buildings, with site-wide infrastructure upgraded to handle the increased power demand and data connectivity. The expansion also incorporated sustainability elements such as rainwater harvesting, rooftop solar integration, and energy-efficient lighting systems. Once fully operational, the Giga Texas expansion will elevate the site's role as a central node in Tesla's manufacturing network, significantly increasing output across vehicle, battery, and structural component lines, while embedding advanced automation and vertically integrated production strategies into the facility's growing footprint. American Dream Miami is an unprecedented megaproject designed to become the largest retail and entertainment complex in the United States. Located in northwest Miami-Dade County, the development spans hundreds of acres and merges commercial, recreational, and hospitality functions into a single, integrated site. The scale and ambition of the project require immense planning, phased construction sequencing, and coordination across multiple engineering disciplines including site civil works, structural engineering, vertical construction, and specialized systems for water management, traffic circulation, and energy efficiency. Site development began with mass grading and the relocation of existing utilities, involving the movement of millions of cubic yards of earth to create a stable foundation across what was once undeveloped wetlands and farmland. Environmental mitigation was a critical early phase component. Stormwater management systems were engineered with massive retention ponds, underground vaults, and bioswales to comply with South Florida Water Management District regulations. Sheet piling, soil stabilization with lime or cement treatments, and perimeter berm construction were necessary to prepare the site for heavy vertical loads and to ensure long-term ground stability, especially for areas designated to house water parks, ski slopes, and multi-story structures. The project's structural layout includes a network of interconnected buildings varying in height and use. Foundations for these buildings were engineered with both shallow and deep systems, depending on geotechnical conditions. Large-span structures like indoor amusement parks, water parks, and retail atriums required specialized deep-pile foundations to resist settlement and lateral movement. Steel framing with long-span trusses was employed extensively to create the large open interiors essential for attractions like roller coasters and wave pools. These components were fabricated off-site and assembled using heavy-lift cranes with precise sequencing to minimize schedule conflicts and allow concurrent work across multiple zones. Mechanical, electrical, and plumbing systems were designed to support massive peak loads generated by climate-controlled recreational areas, retail tenants, and food service zones. Chilled water systems with rooftop cooling towers, variable air volume handlers, and extensive ducting networks were installed to maintain climate conditions in enclosed amusement environments. Plumbing systems had to accommodate both typical domestic demand and specialized functions like indoor snowmaking and large-scale aquatics, necessitating high-capacity pumps, filtration systems, and corrosion-resistant piping. Exterior cladding and roofing systems were selected for both performance and branding, with components such as tensioned fabric structures, glass curtain walls, and themed facades constructed using modular prefabrication techniques. Waterproofing and insulation were layered to account for Florida's heat, humidity, and storm events, with roof drains and overflow systems engineered to handle extreme rainfall. Vertical transportation systems including high-capacity elevators, escalators, and people movers were integrated throughout the development to ensure accessibility and circulation for tens of thousands of daily visitors. Parking infrastructure was another engineering feat. Multi-level garages and expansive surface lots were constructed using post-tensioned concrete decks and cast-in-place retaining walls. Traffic engineering played a central role in designing ingress and egress routes, integrating on-site roads with regional highways through new interchanges, signalized intersections, and bus terminals. Intelligent traffic systems, signage, and wayfinding elements were planned with simulation-based modeling to prevent congestion and facilitate smooth vehicular and pedestrian movement. Construction logistics for American Dream Miami required a scale of coordination typically reserved for industrial megaprojects. Material delivery schedules, workforce housing, staging zones, crane paths, and safety barriers were modeled in 4D simulations to ensure optimal site utilization and risk mitigation. Simultaneously, environmental monitoring was carried out to assess air quality, water runoff, and noise levels, with mitigation strategies applied continuously during active phases of work. Once operational, the facility is designed to handle millions of visitors annually, with systems in place for emergency response, life safety, and operational redundancy. The construction of American Dream Miami reflects the most complex integration of vertical and horizontal engineering in a commercial setting, representing a new generation of hybrid destination centers that merge entertainment, retail, hospitality, and infrastructure into a cohesive, engineered urban experience. The Port of Long Beach Middle Harbor Redevelopment Project is a large-scale maritime infrastructure initiative aimed at modernizing and consolidating two aging shipping terminals into a single, highly automated, and environmentally sustainable container terminal. Located within one of the busiest ports in the United States, the project enhances cargo handling capacity, operational efficiency, and environmental performance, positioning the Port of Long Beach as a global leader in port technology and green logistics. Spanning over 300 acres, the redevelopment required extensive dredging, land reclamation, structural upgrades, and the implementation of advanced terminal automation systems. The initial phase of the project involved the demolition of obsolete structures, including wharves, cranes, warehouse buildings, and paved storage yards. Asbestos abatement, utility disconnection, and hazardous materials removal were carried out before full demolition could proceed. Controlled demolition methods and water suppression systems were used to mitigate dust and environmental impact. Salvageable materials such as steel, concrete, and timber were sorted and recycled, aligning with the port's sustainability goals. Once the site was cleared, major marine construction began. The waterfront area underwent significant dredging to deepen the berths to accommodate post-Panamax and ultra-large container vessels. Dredging operations used hydraulic cutter suction and clamshell dredges, removing silt and sand to reach depths exceeding 50 feet. Dredged materials were transported to offshore disposal sites or used as fill for land reclamation elsewhere within the harbor. The berths were then reconstructed with reinforced concrete wharf structures supported by large-diameter cast-in steel shell piles driven deep into the subsurface sediments. Each wharf section was designed to support the next generation of ship-to-shore gantry cranes, requiring high-capacity pile caps and deck slabs with post-tensioned reinforcement. Fender systems, mooring bollards, and ship access ladders were installed along the quay wall, meeting international standards for vessel accommodation. The cranes themselves were mounted on embedded crane rails with power and data conduits integrated into the wharf edge, enabling fully electrified operation. Simultaneously, the terminal's backland area was regraded and compacted to create a uniform, high-strength surface for container storage, truck lanes, and support facilities. Paving was done using reinforced concrete designed for heavy axle loads. A network of subsurface utilities, including stormwater drains, electrical conduits, water mains, and fire protection loops, was installed below grade, coordinated through 3D modeling to avoid conflicts and streamline future maintenance. One of the hallmark features of the Middle Harbor redevelopment was the integration of automation technology into terminal operations. Automated stacking cranes, guided by a terminal operating system, were deployed in container yards. These cranes operate on fixed rails and are powered by electricity, dramatically reducing emissions and labor costs. Containers are moved between yard stacks and transfer zones, where manned or automated vehicles deliver them to and from ships or trucks. Positioning accuracy, collision avoidance, and task optimization are managed through centralized software, interfacing with container tracking systems and real-time data networks. The truck gate complex was also redesigned to support rapid processing and minimize idling. Optical character recognition, biometric verification, and license plate readers were installed to allow for automated identification and routing. RFID tags on containers and chassis enable seamless integration with the TOS, ensuring drivers are directed efficiently through the terminal. Queue management systems, electronic signage, and automated barriers improve safety and operational flow. The Middle Harbor Terminal was designed with an all-electric infrastructure to reduce its environmental footprint. This included electric cranes, yard tractors, and refrigerated container plug-ins powered by the terminal's shore-based electrical system. Ships docking at the terminal are provided with shore power connections, allowing them to shut down auxiliary engines and eliminate emissions while at berth. Substations and electrical vaults were strategically placed to distribute medium-voltage power throughout the terminal, while redundancy was built in to ensure uptime reliability. Stormwater management was another key environmental component. The redevelopment included construction of biofiltration basins, permeable paving in select areas, and underground detention systems to control runoff. These systems filter pollutants and reduce discharge volume into harbor waters. In addition, lighting systems were upgraded with LED fixtures and dark sky compliant shielding to minimize light pollution and energy consumption. Rail infrastructure was also upgraded to support near-dock intermodal capabilities. New tracks, switches, and crossovers were constructed to tie the terminal into the Alameda Corridor rail network, allowing for the direct transfer of containers between ships and trains without truck drayage. Rail-mounted gantry cranes service the on-dock rail yard, loading and unloading double-stack container trains efficiently while maintaining schedule flexibility. Construction was phased to allow portions of the terminal to come online, while other sections remained under development. Each phase included commissioning and testing of all systems, training of personnel, and calibration of automated equipment. Extensive coordination was maintained with the U.S. Coast Guard, Environmental Protection Agency, and local air quality districts to ensure compliance with safety and environmental regulations. The American Legion Bridge Replacement Project is a major infrastructure effort to replace the aging and overcapacity bridge that carries the Capital Beltway, Interstate 495, over the Potomac River between Maryland and Virginia. The original bridge, built in the early 1960s, is structurally deficient and functionally obsolete due to narrow shoulders, limited capacity, and decades of heavy use. The replacement project involves constructing a modern, wider span that increases capacity, incorporates managed toll lanes, and enhances resilience to future traffic demand and environmental conditions. The construction sequence begins with extensive site preparation on both riverbanks. This includes clearing land for construction staging areas, installing erosion control measures, and conducting geotechnical investigations. Boreholes are drilled along the riverbed and banks to determine subsurface conditions, which informs the design and placement of bridge piers and foundations. Based on these studies, deep foundations using drilled shafts or driven piles are selected to anchor the new structure into stable rock or dense soil layers below the river. To maintain traffic flow during construction, a phased approach is employed. The new bridge is constructed parallel to the existing one, with some segments being built incrementally to allow traffic to shift as work progresses. Temporary trestles and causeways are installed in the river to support construction cranes, concrete pumps, and material transport without disrupting river navigation. The new bridge design features multiple travel lanes in each direction, including high-occupancy toll lanes. The superstructure is composed of pre-stressed concrete girders or steel box girders, depending on span length and navigational clearance requirements. These girders are placed atop reinforced concrete piers that rise from pile caps anchored into the riverbed. Each pier includes icebreakers and scour protection to resist hydraulic forces and sediment erosion. Deck construction involves forming, reinforcing, and pouring cast-in-place concrete slabs with integrated expansion joints and drainage systems. Barriers, lighting, and intelligent transportation systems such as traffic cameras and electronic tolling gantries are embedded into the bridge infrastructure. Noise barriers and aesthetic elements are incorporated to meet community and environmental guidelines. Upon completion of the new bridge, traffic is shifted and the old structure is carefully demolished. This involves cutting and removing steel or concrete elements in segments, using barges and cranes to control debris and ensure environmental compliance. The final phase includes grading, landscaping, and restoring shoreline features impacted during construction, leaving a modern, safer, and more efficient crossing over the Potomac River. The Golden Triangle Polymers project is a significant petrochemical development located in Orange County, Texas, designed to produce polyethylene from ethane feedstock derived from natural gas. This multi-billion-dollar facility includes a world-scale ethane steam cracker and several polyethylene production units, intended to supply high-performance plastic resins for global markets. The project's name is derived from the local region known as the Golden Triangle, a historically industrialized area defined by the cities of Beaumont, Port Arthur, and Orange. Construction of this complex involves massive civil, structural, mechanical, and electrical works, integrating advanced process technologies with robust environmental and safety systems. Site development commenced with bulk earthworks, where tens of thousands of cubic yards of soil were excavated, compacted, and leveled. Ground improvement techniques such as surcharge preloading and deep soil mixing were employed to mitigate settlement risks due to the area's soft, compressible soils and high water table. A dense network of underground utilities, including stormwater drainage, fire water lines, and chemical-resistant process sewers, was installed beneath reinforced concrete foundations that support the heavy process equipment. The ethane cracker, the core of the facility, operates by heating ethane to over 1,500 degrees Fahrenheit in large cracking furnaces. These furnaces were assembled on deep foundations and equipped with radiant coils and convection sections fabricated from high-temperature alloys. The cracked gas is then rapidly quenched to halt the reaction, routed through a series of compressors, and subjected to cryogenic separation processes to isolate ethylene from other hydrocarbons. This required the construction of tall distillation towers, complex heat integration systems, and high-pressure ethylene pipelines, all of which demanded exacting tolerances and strict adherence to process safety protocols. The polyethylene units downstream involve polymerization reactors, pelletizers, and storage silos. Each unit required precise mechanical installation, including the alignment of extruders and gear pumps, supported by large structural steel frameworks and enclosed in metal-clad buildings with integrated ventilation and dust collection systems. Electrical works included high-voltage substations, cable tray networks spanning miles, and process automation systems featuring thousands of field instruments connected to a centralized distributed control system. Construction logistics were coordinated through modularization strategies, with prefabricated pipe racks, equipment skids, and control rooms transported to the site and lifted into position using heavy lift cranes. The facility also features a dedicated rail and truck loading infrastructure for product distribution. Upon completion, the Golden Triangle Polymers project will reinforce the region's standing as a global center for chemical manufacturing, leveraging abundant natural gas resources and state-of-the-art engineering to produce essential plastic materials. Art House in St. Petersburg, Florida, is a contemporary high-rise residential tower designed to bring sophisticated urban living to the downtown waterfront. Rising prominently within the city's growing skyline, this tower combines modern architectural aesthetics with state-of-the-art structural systems and high-end residential amenities. From an engineering and construction standpoint, Art House presents a complex project involving deep foundation systems, vertical construction sequencing, and advanced building envelope technologies tailored to a subtropical coastal climate. The project began with comprehensive site preparation and geotechnical analysis to evaluate subsurface conditions typical of coastal Pinellas County. Due to the high water table and relatively soft soils in the area, a deep foundation system was required. Construction teams employed auger-cast piles or drilled shafts, installed using heavy drilling rigs equipped with continuous flight augers, which placed concrete and reinforcing steel deep into the ground to reach stable soil strata. Dewatering operations were necessary throughout foundation work, with well point systems operating continuously to maintain dry working conditions below grade. Once the pile caps and grade beams were completed, the project transitioned to vertical construction, starting with the building's reinforced concrete core. This central structural element was constructed using jump form systems, rising level by level ahead of the floor slabs. Each floor slab was built using post-tensioned concrete, providing long spans and open layouts ideal for luxury condominiums. Structural engineers designed the lateral load-resisting system with shear walls and moment frames to withstand wind pressures consistent with hurricane-prone areas. Mechanical, electrical, and plumbing systems were integrated through centralized vertical risers, with separate zones serving individual residential units. The HVAC system incorporated energy-efficient air handlers, dehumidification components, and smart thermostatic controls. Plumbing systems were pressure-tested at each level, and sound insulation was installed around vertical ducts and pipe chases to maintain acoustic separation between units. The exterior cladding of Art House consisted of a high-performance curtain wall system and impact-rated glass, engineered to provide thermal insulation and wind resistance while maximizing panoramic views. Installation required the use of suspended platforms and tower cranes, with each unit sealed and waterproofed before interior work proceeded. Balcony structures were cantilevered and waterproofed using multi-layer membranes, with drainage integrated to manage Florida's heavy rainfall. Interior finishes followed a high standard, including European cabinetry, engineered hardwood flooring, quartz countertops, and custom lighting. Coordination of trades during the interior build-out phase was tightly scheduled, with finish carpenters, electricians, tile setters, and painters working in controlled sequences to meet aesthetic and performance standards. Fire protection systems, including sprinklers and emergency lighting, were installed and tested in compliance with local and national codes. The amenities level included a pool deck, fitness center, resident lounges, and workspaces, all requiring precise structural coordination to support loads from water, occupancy, and specialized equipment. Mechanical penthouses and service rooms were constructed on the uppermost levels, housing HVAC units, water heaters, and electrical switchgear, all enclosed within louvered screens for both visual appeal and sound attenuation. Logistics for the entire project were managed within the constraints of a dense urban environment. Construction staging, crane placement, material deliveries, and worker access were choreographed daily to minimize disruption to surrounding businesses and pedestrian pathways. Strict safety protocols and regular inspections ensured compliance throughout the build, with attention to stormwater runoff control and debris containment given the proximity to Tampa Bay. The Southeast Connector, officially known as the Southeast Connector Project, is a significant transportation infrastructure initiative located in Reno and Sparks, Nevada. Its purpose is to create a vital arterial roadway linking the southern and eastern regions of the Truckee Meadows area, improving regional connectivity, alleviating congestion, and supporting long-term economic development. The project spans approximately 5.5 miles and crosses environmentally sensitive wetlands, floodplains, and existing utility corridors. Its construction required an integrated engineering approach that accounted for hydrology, geotechnical stability, traffic flow, and environmental stewardship. The first phase of construction began with extensive site clearing and grading across the alignment, which traverses areas of previously undeveloped land, sections of the Truckee Meadows floodplain, and former military installations. To prepare the ground for heavy roadway infrastructure, Over-excavation and recompaction were performed in areas with poor soil-bearing capacity. Geotechnical surveys identified zones requiring ground improvement, particularly in the marshy areas surrounding the northern end of the corridor. Ground improvement techniques included surcharging, wick drains, and the use of geotextile reinforced embankments to control settlement and increase subgrade stability. The roadway was built on a raised embankment for much of its length to prevent inundation during flood events and to allow for effective stormwater management. Structural fill material, including engineered gravel and crushed rock, was placed in compacted lifts to construct a stable road base. The roadway section includes multiple travel lanes in each direction, shoulders bike lanes, and a multi-use path, accommodating both vehicular and non-motorized traffic. Median barriers, traffic signage, and roadway lighting were installed to enhance safety and visibility. One of the defining engineering features of the Southeast Connector is the number of bridges and culverts required to cross watercourses and wetland areas. The most prominent of these is the large bridge over the Truckee River, which required deep foundations using driven steel piles embedded into dense subsurface strata. The superstructure consisted of pre-stressed concrete girders and cast-in-place deck slabs designed to accommodate vehicular loading and seismic activity common to the region. Smaller bridges and box culverts were constructed at wetland crossings to maintain hydrologic continuity and allow for wildlife passage beneath the roadway. A central design consideration was floodplain interaction. The project corridor is situated in a basin that serves as a natural floodplain during extreme weather events. To mitigate flood risk and maintain flood capacity, engineers constructed large stormwater detention basins and conveyance channels adjacent to the roadway. These features are integrated with box culverts and drainage structures designed to manage runoff and attenuate peak flows. Hydraulic modeling was used to design these systems, ensuring that the new infrastructure would not adversely impact downstream properties or ecosystems. Extensive environmental mitigation and habitat preservation measures were integrated throughout the construction. The alignment required the relocation of sensitive species, the restoration of disturbed wetlands, and the preservation of existing vegetation where possible. Wetland mitigation included the excavation and grading of replacement wetland areas, installation of native plant species, and long-term hydrologic monitoring to ensure functional equivalence to the impacted habitat. Erosion control measures such as straw wattles, silt fencing, and temporary detention basins were deployed during construction to prevent sediment discharge into natural waterways. The project also involved the relocation and protection of existing utilities, including water mains, sewer lines, gas lines, fiber optic cables, and power transmission infrastructure. Coordinating these utility adjustments required phased shutdowns and rerouting, which were timed to minimize service disruptions. Underground utility corridors were constructed with reinforced concrete encasement in areas of high traffic loading, and all utility crossings were carefully coordinated with the vertical and horizontal alignment of the new roadway. Intelligent Transportation Systems infrastructure was incorporated into the design to support future traffic management and monitoring. This includes traffic signal controllers, vehicle detection sensors, overhead variable message signs, and camera systems integrated with the Regional Traffic Operations Center. These technologies allow for real-time traffic updates, incident response coordination, and improved safety for corridor users. Pedestrian and cyclist infrastructure was also prioritized. The entire length of the Southeast Connector includes a separated, paved, multi-use path designed for both recreational and commuter use. Grade-separated crossings and protective barriers enhance safety for non-motorized users. Trailheads with parking, lighting, and informational signage were developed at key access points, encouraging public use and improving community connectivity. Construction sequencing was managed to maintain local access, protect environmentally sensitive areas, and ensure continuous progress through seasonal weather changes. Major earthworks were scheduled for dry months, while bridge and drainage construction proceeded during cooler seasons with controlled dewatering and water quality monitoring. Daily inspections and environmental compliance reporting were conducted to maintain adherence to permits and minimize ecological impacts. The O'Hare 21 Terminal expansion is a transformative infrastructure initiative designed to reconfigure and modernize one of the busiest airports in the world, Chicago O'Hare International. This project includes the expansion of Terminal 5, the demolition and complete replacement of Terminal 2, and the construction of 2 new satellite concourses that will be connected via underground pedestrian tunnels. The goal is to increase gate capacity, enhance passenger experience, and integrate international and domestic operations more seamlessly through what will be called the O'Hare Global Terminal. The process began with the expansion of Terminal 5, where the terminal was extended westward to add over 10 new gates. The expansion required major structural modifications, including deep foundation work using drilled shafts to support new concourse areas and jet bridges. Steel framing was erected in phased segments, coordinated tightly with ongoing airport operations to prevent disruption. Precast concrete panels, curtain wall systems, and advanced HVAC installations were used to ensure energy efficiency and expedited construction. Parallel to this, extensive enabling work was initiated for the new terminal core. This involved utility relocation, demolition of old utility tunnels, and excavation for new underground infrastructure. The most logistically demanding component is the future global terminal, which will replace Terminal 2. This new terminal will be built over active airfield areas, requiring a complex system of temporary taxiway realignments, structural decking over existing utilities, and phased demolition strategies to maintain uninterrupted air traffic operations. 2 new satellite concourses are being constructed west of the existing terminals. These concourses require pile-supported foundations due to the poor soil conditions and high groundwater table common to the site. Tunneling operations are underway to connect the new satellites with the main terminal. These tunnels are being bored using pressurized tunnel boring machines that install precast segmental linings as they advance, maintaining ground stability and controlling settlement risk near active runways. Each new terminal and concourse includes integrated baggage handling systems, advanced security screening infrastructure, and provisions for automated people mover expansions. Electrical systems are built with redundant power feeds, backup generators, and modern fire protection systems. The roofing structures are designed with large-span steel trusses to create open, column-free interior spaces, which are then fitted with custom architectural finishes reflecting local cultural themes. Throughout all phases, construction scheduling is meticulously planned using building information modeling and 4D sequencing to coordinate trades, manage passenger flow, and align with federal aviation security protocols. This expansion will not only increase the airport's capacity, but also completely redefine its functionality and resilience. The Northern Corridor roadway projects in Frisco, Texas, represent a comprehensive infrastructure initiative aimed at accommodating the city's rapid growth and enhancing transportation efficiency. With an investment exceeding $200 million, the city is undertaking 10 major roadway construction and improvement projects, encompassing over 65 miles of new and upgraded roadways. These projects are strategically distributed throughout the Northern Corridor, particularly within the expansive Fields development, a 2,500-acre master-planned community. Construction activities began with extensive site preparation, including land clearing, grading, and the installation of erosion control measures to stabilize the terrain. Subsurface investigations were conducted to assess soil conditions, informing the design of robust foundation systems capable of supporting the anticipated traffic loads. Utility relocation efforts were coordinated to ensure uninterrupted services during the construction phases. Key projects include the widening and extension of Panther Creek Parkway, transforming it into a 6-lane divided roadway to improve east-west connectivity. This involved the construction of new pavement sections, stormwater drainage systems, and the installation of traffic signals at major intersections. Similarly, the expansion of Legacy Drive and Fields Parkway required the reconstruction of existing roadways, incorporating additional lanes, medians, and pedestrian pathways to enhance safety and capacity. The Dallas North Tollway is undergoing significant reconstruction, with more than 18 miles of main lanes being widened to accommodate increasing traffic volumes. This complex operation necessitated the use of advanced construction techniques, such as phased construction to maintain traffic flow, the deployment of high-capacity cranes for bridge beam placements, and the implementation of intelligent transportation systems for real-time traffic management. Frisco Street North is being developed as a new 2-lane roadway connecting Universal Parkway to PGA Parkway. This project includes the construction of a new roadway base, asphalt paving, and the integration of signage and lighting systems to meet modern roadway standards. The design also incorporates provisions for future expansion, anticipating continued growth in the area. Throughout the corridor, attention is given to multimodal transportation options. Sidewalks, bike lanes, and shared-use paths are being integrated into the roadway designs, promoting alternative modes of transportation and enhancing community connectivity. Landscaping efforts, including the planting of native vegetation and the installation of irrigation systems, are also underway to improve the aesthetic appeal of the corridors. One Tampa is a high-rise residential tower under construction in downtown Tampa, Florida, set to become one of the tallest buildings on the city's skyline. This vertical development blends luxury condominium living with advanced structural engineering and urban construction logistics, standing as a significant example of high-density residential growth in a city undergoing rapid transformation. Its design calls for a slender tower profile supported by a heavily reinforced core and innovative construction methods to address both aesthetic goals and the complex engineering demands of building tall in a coastal, hurricane-prone environment. The project commenced with demolition and extensive site preparation in a tightly constrained urban setting. Excavation was limited due to surrounding structures and active utilities, requiring precision trenching and the use of engineered shoring systems to prevent soil collapse and protect adjacent property lines. Geotechnical analysis revealed a need for deep foundation systems, leading to the use of drilled shafts that extended well below the surface into competent limestone bedrock. Drilling rigs installed these caissons using slurry stabilization and steel reinforcing cages, followed by high-strength concrete pours to create vertical elements capable of supporting immense axial and lateral loads. With the foundation complete, the superstructure began with the central concrete core, which rises ahead of the surrounding floors. This jump-form core includes elevator shafts, stairwells, and service risers, and serves as the primary lateral load-resisting system. Around the core, post-tensioned concrete floor slabs are poured using flying formwork and edge protection systems, advancing at a pace of approximately one level every 5 to 7 days. Due to the tower's height and slender form, wind tunnel testing and computational fluid dynamics simulations were performed during design, resulting in the inclusion of outriggers and belt trusses at key levels to manage building sway and ensure occupant comfort under wind loading conditions. The building's facade consists of floor-to-ceiling glazing set within aluminum curtain wall panels engineered to resist hurricane-force wind and water intrusion. Each panel is installed from the outside using swing stages and sealed with silicone gaskets and pressure-equalized joints. Balconies are cantilevered from the slab edges and waterproofed using multi-layer membranes, with stainless steel railings and glass balustrades contributing to the tower's clean, modern appearance. Thermal performance and solar control are achieved through low emissivity coatings on all glazing. Mechanical, electrical, and plumbing systems are routed vertically through the core, with separate mechanical zones serving clusters of floors for optimal efficiency. High-efficiency HVAC units with variable refrigerant flow systems, energy recovery ventilators, and integrated building automation systems were installed to minimize energy use while maintaining indoor air quality. Electrical rooms and water risers are designed with redundancy, surge protection, and emergency power capabilities to maintain service continuity during outages. Interior construction is executed in phases as the structure rises. Once floors are enclosed, trades begin rough-in work for electrical, plumbing, and mechanical systems, followed by drywall, flooring, millwork, and finish carpentry. High-end finishes including stone countertops, engineered wood floors, designer lighting, and smart home integration systems are installed to meet luxury market expectations. Amenities such as a rooftop pool, fitness center, lounge areas, and business suites are distributed across podium and upper floors, each requiring specific structural and waterproofing provisions to support occupant loads, heavy equipment, and open water features. Construction logistics are tightly controlled due to the tower's location in a congested downtown area. A tower crane, material hoists, and just-in-time deliveries are coordinated to maintain workflow without obstructing public rights-of-way. A centralized construction management platform tracks progress, safety compliance, and material inventory in real time. The Springfield Rail Improvements Project is a comprehensive transportation infrastructure initiative designed to enhance rail operations, vehicular traffic flow, and safety within the city of Springfield, Illinois. Located along the primary north-south corridor for freight and passenger rail in central Illinois, this project addresses long-standing issues related to at-grade crossings, traffic delays, emergency vehicle access, and community connectivity. It involves the realignment of rail lines, construction of new underpasses and overpasses, installation of modern signaling systems, and the development of consolidated corridors to better manage the coexistence of rail in urban environments. The core of the project is the consolidation of multiple existing rail corridors onto a single, upgraded alignment along the 10th Street corridor, which will serve as the main north-south route for both freight and Amtrak passenger trains. This realignment requires the relocation of tracks previously running along the 3rd Street corridor. As part of this shift, new double-track sections are constructed using continuously welded rail on concrete ties supported by engineered ballast and subballast layers. Subgrade preparation involved excavation to remove unstable soil, replacement with select fill, and compaction to achieve the necessary bearing capacity and drainage properties. The new corridor includes improvements to the track profile, geometry, and elevation to ensure compliance with modern rail standards. Geometric design ensures proper curve radii, super elevation, and grade transitions, accommodating both high-speed passenger operations and heavy freight trains. Drainage systems, including French drains, culverts, and swales, are installed along the right-of-way to protect the track structure and minimize water infiltration. Grade separation is one of the project's defining features. Multiple new underpasses and overpasses are constructed to eliminate at-grade crossings, enhancing both safety and efficiency. These structures include roadway underpasses with retaining walls, bridge decks, and approach embankments. For underpasses, construction begins with temporary traffic rerouting, followed by excavation and the installation of shoring systems such as sheet piling or soldier pile and lagging walls. Reinforced concrete box culverts or beam and slab bridge decks are installed to carry rail lines over the depressed roadways. Bridge abutments are supported by deep foundations, typically drilled shafts or driven piles, depending on subsurface conditions. Concrete formwork, reinforcement, and pour sequencing are closely coordinated to maintain quality control and structural integrity. Stormwater detention basins and pump stations are added near underpasses to manage runoff and prevent flooding during storm events. Signal and communications infrastructure throughout the corridor is upgraded to include positive train control, wayside signals, automatic block signals, and grade crossing protection where crossings remain. Fiber optic cables are laid in conduits adjacent to the track structure, forming the backbone of the communication system. Signal houses are prefabricated and equipped with relay logic, batteries, and interface panels, enabling centralized traffic control and real-time monitoring of train movements. To minimize disruption during construction, much of the work is staged. Temporary shoe fly tracks are built to divert rail traffic around active work zones. These detour tracks are constructed to full structural standards and include turnout switches, ballast, and signal integration to maintain continuity of operations. As permanent infrastructure is completed, trains are shifted onto the new alignment, allowing for the removal of old track and crossings. Environmental considerations are integrated into every phase of the project. Wetlands, drainageways, and wildlife habitats are assessed during design, with mitigation strategies implemented where impacts are unavoidable. Erosion control measures such as silt fencing, seeded slopes, and temporary sediment basins are deployed during earthwork operations. Noise and vibration studies are conducted, leading to the installation of sound walls and the use of ballast mats or resilient rail fasteners near sensitive receptors like residential neighborhoods or historic districts. Public engagement is also a central component, with ongoing coordination between city officials, the Illinois Department of Transportation, and the Federal Railroad Administration. Stakeholder meetings, community briefings, and property owner consultations ensure transparency and allow concerns about property access, construction impacts, and aesthetics to be addressed proactively. In many locations, enhancements to urban design are incorporated into the project, including landscaping, pedestrian pathways, lighting, and public art installations that reflect Springfield's cultural identity. The Springfield Rail Improvements Project also supports broader goals of regional transportation planning. By consolidating rail operations onto a dedicated corridor, the project lays the groundwork for expanded passenger rail service, including future high-speed rail connections along the Chicago to St. Louis corridor. It also facilitates improved freight logistics by reducing delays caused by vehicle-rail conflicts and allowing for higher throughput along a modernized rail line. Construction logistics are tightly managed, with detailed scheduling, traffic control plans, and safety protocols. Equipment staging areas, material stockpiles, and worker access routes are established to reduce interference with local traffic and maintain construction productivity. Work progresses in multiple segments simultaneously, leveraging different contractors and crews to meet project milestones while keeping disruption to the community at a minimum. The Harbor Bridge project in Corpus Christi, Texas, is an extensive civil engineering effort focused on replacing the original through-arch bridge built in the mid-20th century with a modern, cable-stayed structure designed to meet 21st century transportation demands and navigational standards. The new bridge is engineered to span the Corpus Christi ship channel, allowing for increased clearance to accommodate larger cargo vessels entering the port of Corpus Christi while also expanding traffic capacity for roadway users. Construction began with the extensive groundwork necessary to support such a large-scale bridge. This included site clearing, utility relocations, and the construction of temporary access roads and work trestles. Deep foundation work was performed for the main towers, which support the cable-stayed spans. These foundations consisted of drilled shafts extending hundreds of feet into the soil and rock layers below, designed to support the enormous vertical and horizontal loads transmitted from the bridge deck through the cables and into the towers. The main span is being built using the balanced cantilever construction method. Precast concrete segments are fabricated off-site in a dedicated casting yard. Each segment is trucked to the site, lifted into place using specialized cranes or launching gantries, and then secured using high-strength epoxy and post-tensioning tendons. This method allows segments to be added symmetrically from each side of the tower, maintaining equilibrium and reducing the need for temporary supports in the shipping channel. The bridge's superstructure includes two massive pylon towers, constructed using slip-form techniques that allow continuous vertical casting of concrete. These towers rise to over 500 feet above the channel and anchor the array of stay cables that fan out diagonally to hold the deck in place. Each cable consists of multiple high-tensile steel strands, sheathed in protective coverings to resist corrosion in the coastal environment. On either side of the main span, long elevated approach viaducts are being constructed. These consist of precast or cast-in-place concrete girders supported on piers, which in turn rest on pile foundations. Road deck construction includes forming and pouring concrete slabs, installing parapets, expansion joints, drainage systems, and integrating lighting, traffic sensors, and barrier systems. When completed, the new Harbor Bridge will not only be an architectural landmark, but also a critical freight and commuter route engineered to last for over a century under dynamic traffic and environmental conditions. The Port Arthur LNG terminal is a large-scale liquefied natural gas export facility currently under construction along the Gulf Coast in Port Arthur, Texas. This megaproject is designed to transform natural gas into its liquefied state for efficient overseas transport, requiring a complex assembly of process infrastructure, storage systems, marine loading capabilities, and supporting utilities. The site spans hundreds of acres and is being developed in multiple phases, with the initial phase encompassing 2 liquefaction trains, each capable of processing approximately 6.5 million metric tons of LNG per year. The project's scope includes heavy civil works, advanced cryogenic systems, and extensive marine infrastructure, all of which demand high levels of precision and coordination. Construction began with extensive site preparation, involving the clearing of existing vegetation, deep soil stabilization using lime and cement-treated soils, and the installation of dewatering systems to manage the high groundwater levels typical of the Gulf Coast region. Excavation and grading operations ensured the site met the precise elevation and drainage requirements necessary to support the heavy process equipment and prevent flooding during severe weather events. Foundations for the massive liquefaction trains and LNG storage tanks were constructed using deep pile systems, typically involving steel pipe or precast concrete piles driven to depths exceeding 100 feet to reach load-bearing strata. Above these, large reinforced concrete pile caps and slabs provided stable bases for mounting compressors, heat exchangers, and ancillary equipment. The LNG storage tanks themselves are double-walled, full containment structures composed of inner nickel-steel tanks designed to handle cryogenic temperatures and outer pre-stressed concrete shells that offer structural protection and containment in case of leaks. Installation of the liquefaction equipment required precision alignment of turbo expanders, cryogenic heat exchangers, and gas turbines, all interconnected through high-alloy piping systems built to withstand extremely low temperatures and high pressures. Welding and non-destructive testing followed rigorous standards to ensure system integrity, particularly where thermal cycling could induce material fatigue. Marine infrastructure construction included dredging of berths and turning basins, driving of large-diameter mooring and breasting dolphins, and installation of loading arms capable of transferring LNG from the terminal to specialized carriers. Safety systems were integrated throughout the facility, including emergency shutdown valves, gas detection systems, and blast-resistant control buildings. Upon completion, the Port Arthur LNG terminal will serve as a key export hub, contributing significantly to the global LNG supply chain and demonstrating advanced capabilities in industrial-scale cryogenic engineering. Riverfront Plaza in Jacksonville is a transformative redevelopment project situated along the St. Johns River in the heart of downtown. Formerly the site of the Jacksonville Landing, this new urban park and civic space is designed to integrate green infrastructure, community gathering areas, public art installations, and a landmark architectural feature into one continuous waterfront environment. The construction process for Riverfront Plaza is a blend of civil, landscape, structural, and utility engineering disciplines working together to reshape an iconic portion of the city's shoreline while addressing flood control, stormwater management, and long-term resilience. Demolition of the former structures marked the beginning of the project, involving selective deconstruction and recycling of building materials to minimize environmental impact. Once the site was cleared, geotechnical studies identified bearing capacity, soil composition, and potential contaminants from decades of prior development. Remediation work included soil stabilization, compaction, and in some areas, the replacement of substandard fill with engineered material to support hardscaping and load-bearing features. Perimeter erosion control and sediment fencing were installed to protect the adjacent river during earth-moving activities. One of the critical technical challenges was the elevation management of the plaza to accommodate both pedestrian use and flood mitigation. The design incorporates terraced levels and bioswales that direct stormwater away from heavily trafficked zones and toward vegetated catchment areas. Drainage infrastructure beneath the surface includes a network of perforated pipes, underdrains, and retention basins that allow water to percolate through soil media layers, reducing runoff and filtering pollutants before water reaches the river. Hardscape elements such as pathways, amphitheater seating, and event lawns are supported by concrete slabs and modular paver systems laid atop compacted subbases with integrated utility conduits for lighting, irrigation, and power supply. The installation of lighting poles, surveillance equipment, and public Wi-Fi access points was coordinated to minimize trenching and disturbance of landscaped zones. Foundation work for the signature art installation or vertical landmark structure included drilled concrete piers and anchorage systems capable of resisting wind and uplift forces, especially critical given the site's exposure to hurricanes and river breezes. The landscaping phase utilized native and adaptive plant species to create a biodiverse environment that requires minimal irrigation. Soil amendments, root barriers, and subsurface anchoring systems were used to ensure healthy tree growth while preventing root encroachment into hardscape zones. Installation of urban furniture, shade structures, and wayfinding signage followed, executed with precise alignment and coordination to maintain accessibility and sightlines throughout the plaza. Simultaneously, riverfront bulkhead repairs and reinforcements were conducted to address long-term shoreline erosion. These efforts included driving new sheet piles and installing riprap where necessary to stabilize the bank while integrating it visually with the park's design. All construction activities required ongoing coordination with municipal agencies, local businesses, and public stakeholders to manage access, maintain safety, and adhere to schedule constraints. The related Santa Clara project is a major urban development initiative in Northern California, transforming a former landfill site near Levi's Stadium into a dynamic mixed-use district. Envisioned as a dense urban hub blending residential, commercial, retail, entertainment, and hospitality components, the project spans over 200 acres and represents a model of large-scale master planning, sustainable design, and complex site engineering. Given its scale and the geotechnical challenges of building on a capped landfill, the construction of related Santa Clara required significant groundwork before vertical development could begin. Site development began with environmental remediation and geotechnical stabilization. The site had a history as a municipal landfill, necessitating the construction of an engineered cap to seal the waste material and prevent leachate migration. This cap consisted of layers of compacted clay, geomembranes, geotextiles, and protective cover soils. Before any structures could be built, the cap was inspected, reinforced where necessary, and overlaid with an elaborate system of gas venting and groundwater monitoring wells. Methane gas mitigation was a critical component of the design, with horizontal collection pipes, vertical extraction wells, and passive venting systems embedded beneath proposed building footprints. Given the risk of differential settlement on such fill material, structural design strategies emphasize shallow, flexible foundations for low-rise buildings and deep pile-supported foundations for taller structures. Load-bearing elements were designed with settlement tolerances in mind, and slab-on-grade floors were decoupled from building frames using isolation joints and subgrade void forms. All utilities and infrastructure conduits were routed in flexible, jointed systems to accommodate ground movement, with multiple access points for maintenance and inspection. Horizontal infrastructure development was extensive, involving the construction of new roads, water mains, stormwater systems, and electrical networks. The street grid was laid out to prioritize walkability and multimodal access, with curbless shared streets, wide sidewalks, and dedicated bike lanes. Stormwater management relied on a network of bioswales, underground detention vaults, and permeable pavements, designed to meet stringent regional stormwater discharge regulations while promoting on-site infiltration and groundwater recharge. One of the most complex components of the project was the construction of a central utilities plant and microgrid. This facility provides heating, cooling, and electricity distribution across the entire development using a district energy model. Chillers, boilers, thermal storage tanks, and backup generators are housed in a central structure connected to a network of underground utility corridors. These corridors carry chilled water, hot water, and electrical conduits throughout the site, reducing the need for decentralized mechanical systems and improving energy efficiency at scale. As vertical construction commenced, buildings were erected using a range of framing systems tailored to their use and height. Mid-rise residential buildings typically used post-tensioned concrete podiums supporting wood-framed or light-gauge steel superstructures, while office towers and hotels employed structural steel or reinforced concrete frames with shear walls and lateral bracing. Floor slabs were designed for flatness and serviceability, with embedded sleeves and core-drilled openings to accommodate MEP installations. Facade systems across the development included high-performance glazing, precast concrete panels, metal cladding, and fiber cement rain screens, all selected for durability and aesthetic variety. Building envelopes were constructed with continuous insulation, air barriers, and vapor retarders to meet California Title 24 Energy Code requirements. Roofs were equipped with reflective membranes, green roofing elements, and photovoltaic arrays tied into the site-wide energy monitoring system. Interior fit-outs varied depending on building type, but generally featured open-plan layouts with raised access flooring and modular wall systems in commercial spaces. Residential units were built with acoustic-rated wall assemblies, energy-efficient appliances, and low-flow plumbing fixtures. Retail shells were delivered with basic utilities stubbed to tenant spaces, allowing for customization during future tenant improvements. Open space and landscape architecture played a central role in the master plan, with a significant portion of the site dedicated to parks, plazas, and pedestrian corridors. Structural soil cells were installed beneath sidewalks to support street tree root growth and promote long-term canopy development. Irrigation systems used non-potable water sourced from a recycled water facility and monitored by smart controllers for efficiency. Public art installations, integrated lighting, and site furnishings were deployed to enhance usability and identity across the district. Transportation infrastructure included structured parking garages, transit shuttle drop-offs, and future-proofed provisions for autonomous vehicle integration. All parking structures featured EV charging stations, with conduits sized for future capacity increases. Bicycle storage rooms, lockers, and repair stations were incorporated into each block to support active transportation. Throughout construction, logistics were tightly managed to coordinate multiple contractors working across different zones. Site-wide scheduling tools, digital modeling, and construction sequencing simulations ensured that trades did not interfere with each other and that materials were delivered just in time. Erosion control measures, dust suppression systems, and noise barriers were enforced to minimize environmental impacts on neighboring communities and sensitive habitats along the nearby Guadalupe River corridor. Waterline Tower is a super-tall mixed-use skyscraper under construction in Austin, Texas, set to become the tallest building in the state upon completion. Rising over 1,000 feet, it is engineered to combine residential, office, hotel, and retail functions within a single vertical structure, making it one of the most complex high-rise builds in the region. The tower's footprint is situated adjacent to Lady Bird Lake, requiring careful geotechnical planning and foundation engineering due to its proximity to the water and variable subsurface conditions. The construction process began with site clearing, excavation, and the installation of deep foundations. Because of the tower's extreme height and slender profile, engineers opted for a matte foundation supported by drilled piers. These piers are bored hundreds of feet into stable bedrock, reinforced with high-strength steel rebar cages and filled with Tremy concrete. The matte slab above them is a multi-foot thick concrete platform designed to distribute the tower's vertical loads evenly across the pier array. Following foundation work, vertical construction commenced with the use of a high-capacity jump form system to cast the central concrete core. This core houses elevators, stairwells, mechanical shafts, and acts as the primary structural spine resisting lateral loads such as wind and seismic forces. The concrete used in the core is high strength, often exceeding 10,000 psi, and is poured in successive lifts to maintain structural continuity and construction pace. Around the core, a steel and concrete floor framing system is constructed floor by floor. Composite steel beams span outward from the core to perimeter columns, supporting metal decking over which lightweight concrete slabs are poured. Post-tensioning is employed in certain areas to reduce slab thickness while maintaining structural performance. Construction cranes anchored within the building's core assist with vertical material transport and are periodically climbed upward as the tower rises. The facade is composed of a high-performance curtain wall system with floor-to-ceiling glass, aluminum mullions, and integrated sun shading features. The curtain wall panels are pre-assembled and hoisted into place to accelerate enclosure and allow interior fit-out to begin on lower floors, while upper levels are still being built. Mechanical floors, typically located at intervals, house equipment such as HVAC chillers, pumps, electrical switchgear, and water tanks. These are acoustically and structurally isolated to minimize vibration and noise transfer to tenant spaces. The top of the tower includes tuned mass dampers and structural outriggers that tie the core to perimeter columns, increasing lateral stiffness. Overall, Waterline Tower represents an intricate orchestration of advanced engineering, material logistics, and construction management, executed under tight spatial constraints and ambitious scheduling within an active urban environment. The Northeast Lakeview College expansion in New Braunfels represents a major investment in regional higher education infrastructure, aimed at addressing increasing enrollment demands and enhancing accessibility for students across Comal County and surrounding areas. This project involves the comprehensive renovation and adaptive reuse of a pre-existing 58,000 square foot commercial structure, formerly occupied by a financial institution, into a fully functioning academic center designed to support a broad range of instructional programs and student services. Construction activities commenced with selective interior demolition to remove non-load-bearing partitions, obsolete mechanical systems, and outdated finishes. This was followed by structural assessments to ensure the existing building shell could accommodate new loads introduced by academic programming. Reinforcement of floor slabs and roof structures was carried out where necessary, particularly in areas designated for heavy equipment such as laboratory installations and mechanical units. Mechanical, electrical, and plumbing systems were entirely overhauled. A new rooftop HVAC system with variable air volume controls was installed to ensure optimal thermal comfort and energy efficiency across diverse instructional spaces. Electrical upgrades included new panel boards, LED lighting fixtures, and structured cabling to support campus-wide Wi-Fi and integrated classroom technologies. Plumbing infrastructure was expanded to serve additional restrooms, science labs, and break areas, with low-flow fixtures and hot water recirculation systems incorporated to reduce water consumption. Interior build-out included the construction of general-purpose classrooms, computer labs, science laboratories with fume hoods and gas piping, faculty offices, and multi-use student spaces. Specialized instructional areas were outfitted with flexible furnishings, audio-visual systems, and digital teaching tools compatible with hybrid learning formats. Acoustical treatments such as suspended ceiling panels, wall baffles, and sound-isolating doors were used throughout the facility to maintain a conducive learning environment. Accessibility upgrades brought the building into compliance with the Americans with Disabilities Act, including the installation of a new elevator, widened doorways, tactile signage, and accessible restroom facilities. The entry and exit points were redesigned with automated doors and weather protection canopies, and site work improvements included new sidewalks, AD-compliant parking, landscaping, and stormwater management systems. The project also involved the addition of a new fire protection system, including sprinklers and a fire alarm network, fully integrated into the college's safety protocols. Security enhancements included controlled access points, surveillance cameras, and emergency communication systems. Once operational, the expanded Northeast Lakeview College campus in New Braunfels will serve as a vital educational hub, providing state-of-the-art facilities and instructional capacity to support the growing academic needs of the region.
The reconstruction of Tyndall Air Force Base in Panama City, Florida, is one of the largest and most advanced military installation rebuilds in modern U.S. history, driven by the extensive damage caused by Hurricane Michael in 2018. This reconstruction effort represents a long-term, multi-phase infrastructure and facilities redevelopment plan centered on resilience, mission readiness, and advanced technology integration. Designed to support next-generation fighter aircraft like the F-35, the effort required a complete reimagining of the base's built environment, including structural systems, utilities, flight line infrastructure, and storm-hardened facilities. Initial efforts began with damage assessment, site clearance, and debris removal, carried out by joint military and civilian engineering teams. Buildings deemed unsalvageable were demolished in a controlled sequence, with materials sorted for recycling or disposal. Simultaneously, civil engineers conducted a comprehensive geotechnical and hydrological survey across the installation to inform the design of new structures, utility corridors, and stormwater management systems. Much of the soil had to be reconditioned or replaced due to saturation and compaction caused by the storm, requiring stabilization techniques such as lime treatment, compaction grouting, and subgrade reinforcement using geosynthetics. The master plan for the rebuilt base incorporated distributed utilities, redundant systems, and hardened structures. Electrical infrastructure was placed underground where feasible to reduce vulnerability to wind and debris. Water, sanitary sewer, and communications networks were reconstructed using corrosion-resistant materials, with looped layouts allowing for continuous service during partial outages. Substations, lift stations, and control buildings were housed in wind and flood-resistant enclosures built to withstand Category 5 hurricane conditions. Vertical construction emphasized hardened concrete and steel structures with progressive collapse resistance, blast resistance, and full compliance with unified facilities criteria. Aircraft hangars were designed with clear spans exceeding 200 feet, supported by structural steel frames and braced bays. Roof assemblies used standing seam metal over insulated decking systems anchored with high-load mechanical fasteners and uplift rated to survive extreme wind events. Maintenance bays, munitions storage, and logistics centers were outfitted with reinforced concrete walls and storm-rated doors, ensuring continuity of operations during adverse conditions. Flight line reconstruction involved complete resurfacing of taxiways and aprons, the addition of new lighting systems, jet blast deflectors, and improved stormwater drainage. Concrete pavements were installed over stabilized subbases with expansion joints and reinforced panels capable of supporting repeated F-35 operations. Navigational aids and radar systems were relocated and shielded for increased survivability, while air traffic control towers were rebuilt with hardened glazing and backup power systems. Administrative and residential facilities were constructed with modular, energy-efficient designs, incorporating passive solar features, high-performance insulation, and low-impact development strategies. Barracks, dining facilities, and command buildings included progressive energy systems like solar photovoltaic arrays, advanced building management systems, and high-efficiency HVAC systems. Smart base technology was embedded throughout, including automated access control, video surveillance, and integrated cybersecurity protocols governing building automation and mission-critical systems. Logistics for the reconstruction were coordinated under a hub-and-spoke model, with central material laydown yards, controlled access zones, and precision delivery scheduling to manage the flow of construction equipment, materials, and personnel. Construction was executed in overlapping phases to allow ongoing base operations, requiring strict safety and coordination protocols. Federal, state, and local permitting was streamlined under mission priority guidelines, with environmental compliance maintained through on-site inspectors and adaptive sedimentation control measures.
The redevelopment of Terminal 1 at John F. Kennedy International Airport is a major aviation infrastructure initiative designed to transform the aging terminal into a state-of-the-art global gateway. Scheduled for completion in 2025, the new Terminal 1 will significantly expand capacity, modernize facilities, and enhance the passenger experience through a comprehensive overhaul of terminal architecture, airside and landside access, and critical systems. This $9.5 billion project is being constructed on the sites of the former Terminal 1, Terminal 2, and the former Terminal 3, requiring an intricate phased demolition and construction process to keep the airport operational throughout the redevelopment. The first major phase involved the demolition of old structures, including the entirety of Terminal 2. Given the operational context of an active airport,
Demolition was performed in a highly controlled environment. Work included asbestos abatement, removal of outdated mechanical systems, and structural dismantling carried out in sequenced zones to maintain safety and minimize impact on adjacent runways and taxiways. Materials were sorted for recycling and disposal, with concrete crushed on site for reuse as fill-in subgrade construction. Following demolition, site preparation included soil stabilization and grading across the expansive redevelopment footprint. The new terminal is built on a reinforced mat foundation system, consisting of deep piles socketed into dense subsoil layers to counter settlement and lateral loads. Pile caps and ground-level slabs were poured in stages, using high-strength concrete and admixtures tailored to airport-grade durability requirements. Ground improvement techniques, including vibrocompaction and surcharge preloading, were employed to stabilize, fill, and mitigate long-term settlement risks, especially in areas adjacent to active taxiways. The superstructure of the terminal is being constructed with a combination of steel framing and reinforced concrete cores. The design emphasizes long-span steel trusses in the main check-in hall and departure areas to allow for wide-open spaces without intermediate columns. These trusses are fabricated off-site and erected using crawler cranes during low traffic periods, coordinated with Port Authority and air traffic control to maintain safety. Reinforced concrete shear walls and elevator cores provide lateral stability and house the terminal's mechanical and vertical transportation systems. The new Terminal 1 will span over 2 million square feet, incorporating up to 23 wide-body aircraft gates upon full build-out. To accommodate this, the apron and aircraft parking areas are being reconstructed with concrete pavements rated for Group 5 and 6 aircraft. Subsurface drainage systems, fuel hydrant lines, and de-icing fluid containment infrastructure are being installed beneath the apron. Jet bridges, preconditioned air systems, and ground power units are integrated into each gate position to streamline aircraft turnaround operations and reduce emissions. The terminal building itself is designed with a high-performance facade, using double-glazed curtain wall systems with low emissivity coatings and integrated sunshades. These systems not only reduce solar heat gain, but also create a visually open and naturally lit interior environment. Roof structures are insulated and built to accommodate photovoltaic panels, contributing to the terminal's sustainability goals. Inside, the passenger processing zones are being built with modular and flexible layouts. The check-in hall includes self-service kiosks, bag drop counters, and high-capacity conveyor systems feeding into a next-generation baggage handling system. This system uses automated sorters, inline explosive detection machines, and robotic diverters to ensure both security and efficiency. The departures area includes centralized security screening with advanced CT scanners and automated tray return systems. The terminal's concourses are being built to accommodate retail, dining, and lounge spaces along with circulation corridors. Structural framing is designed to allow flexibility for future reconfiguration, with raised floors in select areas to support changes in mechanical and electrical distribution. Passenger movement is facilitated by moving walkways, elevators, and escalators, while lighting, air conditioning, and signage systems are controlled by a centralized building management platform. Mechanical, electrical, and plumbing systems are distributed from dedicated utility rooms located in basement and rooftop levels. The HVAC system includes high-efficiency chillers, thermal storage tanks, and air handling units with demand-controlled ventilation. Plumbing systems are outfitted with leak detection, low-flow fixtures, and hot water recirculation pumps to reduce consumption. Electrical infrastructure includes dual power feeds from independent substations, backed by diesel generators and battery storage systems for uninterruptible power supply to critical systems such as air traffic communications, baggage handling, and security equipment. Landside access is being completely reconfigured as part of the redevelopment. This includes new roadways for private vehicles, commercial transport, and shuttle buses, along with expanded curbside drop-off and pickup zones. New parking structures are being built with integrated wayfinding, EV charging stations, and real-time space monitoring systems. Pedestrian bridges are constructed to link parking and transit hubs directly with terminal levels, allowing safe and efficient passenger flow across busy traffic zones.
Empire Wind is a major offshore wind development located in the Atlantic Ocean off the coast of New York, aimed at delivering renewable energy directly into one of the most power-demanding regions of the United States. The project is being constructed in two phases, known as Empire Wind 1 and Empire Wind 2, together comprising several gigawatts of capacity. The wind farm is situated in the New York Bight, in a federally designated wind energy area stretching between 15 and 30 miles south of Long Island. The engineering scope of this project is immense, involving marine logistics, heavy structural fabrication, subsea electrical installation, and coastal infrastructure upgrades. Construction began with extensive marine geophysical and geotechnical surveys to assess the ocean floor. These surveys utilized sonar and core sampling to determine sediment composition, load-bearing capacity, and potential obstructions. Based on the findings, monopile foundations were selected for the turbines. These are large steel cylinders, some over 30 feet in diameter and hundreds of feet in length, driven deep into the seabed to support the massive towers and nacelles. Pile driving is conducted using dynamic hammers aboard specialized jack-up vessels that anchor to the seafloor during operations. The wind turbines, each rated at over 10 megawatts, consist of a steel tower, nacelle housing the generator and gearbox, and 3 rotor blades, each longer than a football field. These components are pre-assembled at coastal staging areas and transported by heavy lift installation vessels. Once at sea, cranes aboard these vessels lift and assemble the components in stages. First the monopile, followed by transition pieces, then towers, nacelles, and finally blades. Each turbine is connected to an offshore substation via inter-array cables buried into the seabed using jet plows or cable plows. The substations transform the voltage and transmit power through export cables back to shore. These export cables, which are also buried to protect against anchors and trawling, make landfall at pre-engineered transition points. Onshore, electrical substations are constructed to receive and further convert the power before it enters the regional grid. These substations include switchgear, transformers, and reactive compensation equipment to manage voltage stability. Simultaneously, the operations and maintenance facility is built at the port, featuring docking facilities for crew transfer vessels, storage for spare parts, and remote monitoring systems to track turbine performance in real time. Every stage is synchronized for logistical efficiency, environmental compliance, and long-term operational resilience. Brightline West is a high-speed rail project under construction with the goal of connecting Las Vegas, Nevada to Rancho Cucamonga, California. Designed to reduce vehicle congestion on the I-15 corridor, the system is being engineered for electric trains capable of operating at speeds up to 200 miles per hour. The entire route spans approximately 260 miles and is being built primarily within the median of the I-15 highway, which presents unique logistical and structural engineering challenges. The first major phase of construction involves extensive right-of-way preparation. Since the alignment runs along an existing highway corridor, engineers must stabilize soil and regrade the median to accommodate double-track guideways. Excavation equipment is used to dig trenches and remove unsuitable soil, which is then replaced with compacted aggregate layers to form a solid base. Drainage systems are installed concurrently to prevent water accumulation and erosion beneath the future track. Concrete slab track construction is favored over traditional ballasted track due to its lower maintenance requirements and stability at high speeds. Precast or cast-in-place concrete track beds are laid with precision alignment to maintain tight tolerances for rail geometry. Continuously welded rail is installed atop these slabs using embedded fastener systems, which reduce vibration and noise while securing the rails rigidly. Bridge structures are required at various highway interchanges, flood zones, and wildlife crossings. These are built using deep foundations, such as driven piles or drilled shafts, with superstructures formed from precast concrete girders or cast-in-place box segments. Temporary falsework and heavy cranes are used extensively during this phase to hoist components into position. Stations are being designed with elevated platforms, intermodal access, and parking structures. Construction here includes deep excavation for utilities, elevator shafts, and escalator systems. Steel framing and curtain wall systems form the structural and architectural envelope of the terminals. Power delivery is achieved through an overhead catenary system. Substations convert utility power to the necessary voltage for high-speed traction. The catenary poles are installed at regular intervals with tensioning devices to maintain wire elevation and consistency. The East Blackland Solar Project, located in Travis County, Texas, is a utility-scale photovoltaic power generation facility designed to harness solar energy through the deployment of high-efficiency solar panels across several hundred acres of land. The project is part of a broader strategy to expand renewable energy capacity in Central Texas and contributes to grid reliability and emissions reduction targets by providing clean electricity to the regional power market. Construction of the facility began with comprehensive site assessments to evaluate solar irradiance, soil stability, drainage patterns, and potential environmental impacts. Land preparation included grading to create a uniform slope for optimal panel alignment, followed by the installation of erosion control measures, such as silt fences and retention basins to manage stormwater during construction. Once the site was cleared and stabilized, trenching operations commenced to lay underground conduit for power and communications cabling, which would later connect the solar arrays to inverters and switchgear. The racking systems, which support the photovoltaic panels, were constructed using galvanized steel posts, driven into the ground at regular intervals. These posts were installed with hydraulic pile drivers calibrated to maintain precise verticality and depth. The project utilized single-axis tracking technology, which allows solar panels to follow the sun's path across the sky, thereby maximizing energy production. The tracking systems were assembled on the support structures and equipped with actuators and controllers programmed to adjust panel tilt based on real-time solar position data. Photovoltaic modules were mounted in rows on the racking systems with electrical connections made in series to form strings, which were then aggregated into combiner boxes. From there, direct current electricity was routed through underground cables to centralized inverter stations, where it was converted into alternating current. Each inverter station included transformers, switchgear, and protective relays designed to manage voltage regulation, grid synchronization, and fault protection. A high-voltage substation was constructed on site to step up the electricity to transmission-level voltages and interconnect it with the local utility grid. This substation included power transformers, circuit breakers, and transmission line takeoff structures, all built to utility specifications. The entire site was enclosed with security fencing and equipped with monitoring systems, including weather stations and real-time data acquisition platforms that allow operators to track performance metrics and remotely manage the system. Upon completion, the East Blackland Solar Project became a key renewable energy asset for the region, demonstrating the scalability and reliability of solar technology in utility applications and supporting the ongoing transition toward a more sustainable energy infrastructure. The Sunrail Northern Extension to DeLand is a significant commuter rail infrastructure project expanding Central Florida's regional transportation network beyond its current northern terminus in DeBary. This extension involves upgrading an existing freight corridor owned by a Class I railroad to accommodate both passenger and freight operations. A complex endeavor requiring careful coordination, advanced civil engineering, and robust rail construction practices. Stretching approximately 12 miles, the extension is engineered to support high-frequency commuter trains while integrating with existing signaling, communications, and control systems already in operation along the rest of the Sunrail corridor. Construction began with comprehensive surveying and subsurface utility engineering to identify and avoid conflicts with buried infrastructure such as fiber optic lines, drainage culverts, and utilities paralleling the right-of-way. Track bed preparation commenced with clearing, grubbing, and regrading of the rail corridor to ensure proper drainage and subgrade stability. Where required, Sub-ballast layers were improved or replaced using geotextiles and compacted granular material to ensure sufficient load-bearing capacity and long-term durability of the rail track structure. The single mainline track was upgraded using continuously welded rail, CWR, installed on concrete ties spaced and seated within a new bed of granite ballast. Rail sections were thermite welded in the field, followed by grinding and alignment to ensure smooth operation and minimize vibration. Ballast was placed in multiple lifts and tamped using automated machines that aligned and leveled the rail geometry to industry tolerances. Turnouts and crossovers were added strategically to allow passing operations and access to sidings, especially where freight and passenger train scheduling could potentially overlap. Bridge structures along the route, including culverts and overpasses, underwent inspection and, where necessary, rehabilitation to meet the higher loading standards required for passenger rail. Structural upgrades included concrete spall repair, bearing replacement, and in some cases, full superstructure reinforcement using steel plate bonding or carbon fiber wrap techniques. At-grade crossings were upgraded with new concrete panels, signal gates, and advanced train detection systems linked to positive train control, PTC infrastructure, to enhance safety and comply with federal mandates. The extension's new terminus at DeLand required the construction of a new passenger platform, parking area, and supporting infrastructure. The platform was built using precast concrete components, featuring tactile warning strips, lighting, canopies, and ADA-compliant ramps. Electrical and communications conduits were installed beneath the platform for future scalability. Adjacent facilities included a drop-off loop, pedestrian walkways, security systems, and stormwater management features designed to handle Florida's frequent rainfall. Signal system integration was a critical component of the project. Wayside signals, interlockings, and block detection systems were installed or modified along the route to provide seamless connectivity with the central dispatching system already managing Sunrail operations. Fiber optic cable was trenched along the corridor to provide real-time data transmission for PTC, train location monitoring, and emergency communication systems. Signal bungalows were prefabricated and installed on elevated concrete pads with backup power supplies to ensure system reliability during severe weather events. Construction operations were staged to minimize disruptions to existing freight traffic, requiring off-peak and nighttime work windows, flagging crews, and coordination with the freight operator to sequence activities without causing operational delays. Environmental protection measures were enforced throughout, including erosion control, wildlife protection plans, and careful management of work within wetlands and flood-prone areas. Permitting with state and federal transportation and environmental agencies was ongoing and comprehensive, reflecting the complexity of modifying an active rail corridor for dual-use functionality. Upon completion, the Sunrail Northern Extension to DeLand will provide vital transit connectivity to Volusia County, enhancing regional mobility while relieving highway congestion. The construction of the Intel semiconductor fabrication plant in Arizona, part of a multi-billion-dollar investment in domestic chip production, is a highly advanced industrial project that combines precision engineering, extreme cleanliness requirements, and massive mechanical and electrical infrastructure. Situated at Intel's existing Ocotillo campus in Chandler, this expansion adds new fabs to one of the most technologically sophisticated manufacturing sites in the world. The project supports Intel's strategy to enhance U.S. semiconductor capacity and resilience in the global supply chain, and involves the creation of highly specialized cleanroom space, support buildings, and utility systems capable of sustaining the rigorous demands of advanced chip fabrication. Site development began with large-scale excavation and grading to accommodate multiple large-footprint buildings, including cleanroom facilities, utility plants, and administrative structures. Subsurface conditions in the desert environment required over-excavation and replacement with engineered fill
to achieve the uniform settlement and load-bearing capacity needed for precision manufacturing operations. Thousands of deep foundation elements, including auger cast piles and drilled piers, were installed beneath the fab buildings to isolate them from vibration and thermal expansion, both of which can interfere with nanometer-scale semiconductor production. Above the foundation level, a reinforced concrete mat slab was poured to provide a base for the fab. This slab required an extremely flat and level surface finish, with tolerances far exceeding those used in conventional construction. Specialized concrete mixes were used to control shrinkage and thermal cracking, with continuous placement operations and finishing conducted under tightly controlled environmental conditions. The superstructure of the semiconductor fab buildings was constructed using a combination of steel framing and reinforced concrete walls, designed to support the heavy mechanical loads and provide a rigid frame for the cleanroom environment. The cleanroom floors were constructed using raised access systems, which allow for the routing of process utilities, electrical conduits, and airflow distribution beneath the floor surface. These systems are supported by structural steel decks designed to limit deflection and vibration to imperceptible levels. One of the most complex aspects of the Intel fab construction is the integration of its process support infrastructure. Semiconductor manufacturing requires ultra-pure gases, deionized water, high-voltage electrical power, vacuum systems, and chemical waste handling, all of which must be delivered and maintained with absolute precision. Gigantic central utility buildings were constructed adjacent to the fab to house air compressors, chillers, scrubbers, water treatment systems, and gas cabinets. These systems feed into the fab through an intricate network of insulated stainless steel piping, double-walled chemical lines, and redundant electrical feeders, all routed through dedicated utility corridors and mechanical chases. HVAC systems for the fab are designed to maintain cleanroom conditions in accordance with ISO Class 1 to Class 5 standards, depending on the process zone. These systems involve massive air handling units that filter air through high-efficiency particulate air and ultra-low penetration air filters, delivering laminar airflow through the cleanroom ceiling. Air change rates are among the highest of any building type, and temperature, humidity, and particulate levels are continuously monitored and adjusted by automated building management systems. The cleanrooms themselves are modular in construction, with prefabricated panels used to form walls, ceilings, and integrated air plenums. Interior finishes are composed of non-shedding, electrostatically dissipative materials that resist chemical corrosion and minimize contamination risk. Workers must pass through multi-stage gowning areas, air showers, and decontamination chambers before entering these spaces, and construction crews must follow similar protocols during the fit-out phase. Electrical infrastructure is equally critical, as semiconductor fabs consume vast amounts of power with a need for extremely reliable delivery. On-site substations, switchgear, uninterruptible power supplies, and emergency generators are installed in layered configurations to support continuous operation. Power quality is managed through real-time monitoring and conditioning systems to prevent voltage fluctuations or outages that could compromise sensitive fabrication tools. Process tool installation represents a major component of fab construction. These tools, which include photolithography scanners, etchers, ion implanters, and chemical vapor deposition chambers, are extremely sensitive and must be installed on vibration-isolated foundations with precise alignment. Tool hookup involves hundreds of connections for process gases, liquids, vacuum, and data communications. Each tool is commissioned individually and tested extensively before being certified for production. To manage water use, the site features a cutting-edge water reclamation plant that recycles process water for reuse in cooling towers and rinse processes. This system is critical in Arizona's arid climate and is one of the most advanced water sustainability efforts in industrial manufacturing. Waste treatment systems also neutralize and separate chemical byproducts for proper disposal, in compliance with federal and state environmental regulations. Construction was carried out using lean methodologies and building information modeling, enabling real-time coordination between trades and minimizing clashes between complex mechanical systems. Prefabrication was employed extensively for piping racks, electrical skids, and modular wall panels to accelerate installation and reduce site congestion. With thousands of workers on site daily, Logistics were managed using zone scheduling, digital tracking, and real-time communication tools to maintain progress and safety.
The Sequoia Solar Farm is a utility-scale photovoltaic power generation facility designed to produce hundreds of megawatts of renewable energy in a desert environment. The project spans thousands of acres and involves the installation of hundreds of thousands of solar photovoltaic modules, arranged in meticulously engineered arrays to maximize solar capture and energy output across seasonal variations. Construction begins with extensive site grading and preparation, ensuring a level and stable surface to accommodate the massive racking structures. The native soil is compacted and sometimes augmented with imported fill or geotextile fabric in areas requiring enhanced stabilization. The first major task involves driving steel piles into the ground to serve as foundations for the solar racking systems. These piles are typically driven to depths of 8 to 12 feet using pile-driving rigs calibrated to maintain consistent verticality and spacing. The racking systems are either fixed tilt or, more commonly in this project, single-axis trackers. Single-axis trackers are mechanically driven systems that rotate the solar panels to follow the sun's movement throughout the day, increasing energy capture by 20 to 30% compared to fixed systems. Following racking installation, photovoltaic modules are mounted in strings, often composed of up to 20 panels per row. Technicians bolt each module to the racking frame and connect them using standardized plug-and-play wiring systems. These module strings feed into combiner boxes distributed across the site. From there, direct current electricity flows into centralized inverters, which convert it into alternating current suitable for grid use. Electrical cabling is routed in underground trenches that are excavated using trenchers or chain-driven trenching machines. These trenches are backfilled with sand or thermal backfill to ensure heat dissipation and electrical insulation. Medium voltage transformers are placed at strategic intervals and mounted on concrete pads to boost the voltage for transmission. These are connected to a substation located at the perimeter of the farm, which aggregates all power generated and steps up the voltage for injection into the regional electrical grid. To ensure efficiency and longevity, each component of the system, modules, trackers, inverters, and transformers, is monitored via a SCADA system. This system collects real-time performance data, enabling operators to identify underperforming strings, inverter faults, or shading issues due to dust accumulation. The entire farm is encircled with fencing and access-controlled gates, and interior access roads are constructed using compacted gravel to allow maintenance vehicles year-round access. The Waterline Tower in Austin, Texas, is an ambitious high-rise construction project that, upon completion, will become the tallest building in the state. Rising to a height exceeding 1,000 feet, this mixed-use skyscraper is engineered to accommodate residential units, a luxury hotel, office spaces, and retail areas, all within a compact downtown footprint adjacent to Lady Bird Lake. The complexity of the tower's design and construction stems from its height, slender profile, and the integration of diverse occupancy types across its vertical structure. Initial construction began with deep excavation and shoring to enable installation of a mat foundation capable of distributing immense structural loads across Austin's variable limestone and clay subsoils. Foundation work included the drilling of reinforced concrete piers extending more than 100 feet into bedrock, coupled with a heavily reinforced concrete mat that was poured in a single continuous operation, requiring logistical coordination of multiple concrete batch plants and continuous pumping over several days. The building's superstructure is composed primarily of a high-strength reinforced concrete core, which houses vertical transportation systems and provides torsional stability against wind and seismic forces. Outrigger and belt truss systems are integrated at mechanical levels to distribute lateral loads across the perimeter columns, enhancing structural rigidity. The core was constructed using a self-climbing formwork system, allowing for continuous vertical progress without reliance on external scaffolding, while steel and concrete composite floor systems were constructed simultaneously to minimize schedule duration. Mechanical, electrical, and plumbing systems are vertically stacked in dedicated shafts with strategically located mechanical floors to ensure efficient distribution and maintenance access. High-efficiency chillers, low-flow plumbing fixtures, and advanced lighting controls are integrated as part of the building's sustainable design approach, targeting LEED certification. Horizon West Bay in Largo, Florida is a mid-rise residential development constructed to deliver contemporary living accommodations within a growing suburban city center. Located near municipal and civic facilities, this project is emblematic of the new wave of urban-style residential buildings being introduced to smaller cities throughout the Sun Belt. The development integrates multiple levels of residential units with ground floor amenities and structured parking, requiring the coordinated use of mixed-use construction strategies, efficient structural systems, and infrastructure integration specific to the local climate and regulatory conditions. Construction began with extensive site clearing and grading, followed by geotechnical investigations to determine the bearing capacity of the underlying soils. Given the relatively flat terrain and shallow water table in the Largo area, slab-on-grade construction was ruled out for the upper levels, necessitating a more complex foundation solution. Engineers selected either shallow spread footings or a combination of grade beams and driven piles to support the superstructure, depending on the location within the site and the anticipated load distribution. Subsurface utility relocation was required early in the project, especially where stormwater drainage and sewer infrastructure intersected the future building footprint. Once the foundation was laid, construction transitioned to the vertical structural elements. Horizon West Bay employed concrete masonry unit, CMU walls, for structural partitions and exterior load-bearing components, combined with cast-in-place concrete slabs and precast concrete plank systems. This hybrid construction method balanced strength, cost efficiency, and fire resistance. Interior framing for unit walls and ceilings used metal studs and light-gauge steel tracks, allowing for faster mechanical and electrical installation across units. Mechanical systems were designed to accommodate Florida's humid climate, with each unit receiving a dedicated HVAC system featuring energy-efficient heat pumps, advanced filtration, and humidity control. Plumbing and electrical risers were centralized for ease of maintenance and constructed with noise-dampening measures to minimize acoustic transmission between floors and adjoining units. Fire safety systems included fire-rated walls, smoke alarms, sprinklers, and pressurized stairwells to meet all life safety codes for multifamily buildings. The building envelope was constructed with stucco-finished IFS cladding over a weather-resistive barrier, installed in layers to achieve both aesthetic appeal and energy performance. Window and door systems used insulated, low-emissivity, impact-rated glass to meet hurricane resistance codes while providing thermal efficiency. Roof systems incorporated rigid insulation and a reflective membrane to reduce heat gain and meet Florida's energy standards. Interior work proceeded as each floor was dried in, beginning with MEP rough-ins followed by drywall, flooring, cabinetry, and finish carpentry. Flooring materials included luxury vinyl plank and tile, selected for durability and ease of maintenance. Kitchens and bathrooms were fitted with solid surface countertops, undermount sinks, and energy-efficient fixtures. Common areas such as lounges, fitness rooms, and mail rooms were completed in tandem with residential units to ensure functional amenities at the time of occupancy. Structured parking was integrated into the building footprint, constructed using precast concrete panels and beams with a traffic-bearing waterproofing membrane. Lighting, security systems, and access control were embedded throughout the garage to ensure safety and usability. Site improvements included sidewalks, landscaping, stormwater detention ponds, and lighting fixtures designed for dark sky compliance. Civil engineering played a key role in integrating the development into Largo's municipal stormwater and transportation networks.
The expansion of the Tesla Gigafactory in Austin, Texas, officially known as Giga Texas, represents one of the largest and most advanced industrial construction efforts in the United States. Located along the Colorado River on the eastern edge of Austin, the site spans over 2,000 acres and serves as a central hub for Tesla's vehicle manufacturing, battery production, and future operations related to its energy and robotics divisions. The expansion of this facility has required large-scale site development, precision engineering, and massive logistical coordination to accommodate the simultaneous construction of multiple production lines and infrastructure systems. Site work began with extensive earth-moving operations to level the vast tract of land and prepare it for heavy industrial use. Bulldozers, scrapers, and excavators were used to move millions of cubic yards of soil, creating a flat and stable platform for foundations. Drainage swales, detention ponds, and underground stormwater systems were installed early in the process to manage runoff and prevent flooding, especially given the site's proximity to the river and its location within a region subject to periodic heavy rainfall. Foundation work for the expanded areas of the Gigafactory involved deep excavation and the construction of reinforced concrete footings, grade beams, and mats, due to the sheer size and weight of the industrial equipment housed within the plant, including stamping presses, casting machines, and robotic assembly lines. Foundations were engineered to extremely tight tolerances. Concrete was poured in large, continuous placements using high-performance mixes designed for strength and durability. Reinforcing steel cages were pre-tied on-site and lifted into place using tower cranes, ensuring consistency and efficiency in the foundation builds. The superstructure of the Gigafactory expansion primarily consists of a steel frame system with large-span girders and open-web joists designed to create wide, column-free interior spaces. This framing approach allows for maximum flexibility in arranging production lines and material handling systems. Structural steel components were fabricated off-site and delivered in sequenced loads for immediate erection. Multiple cranes operated in parallel to lift and set beams, columns, and roof trusses, with crews bolting and welding connections at a rapid pace to maintain schedule. Roof and wall systems are built with insulated metal panels and reinforced concrete tilt-up walls. The use of tilt-up construction provided a quick and durable solution for enclosing the facility. Panels were cast on site in horizontal beds, then lifted into place using specialized rigs and temporarily braced until tied into the structural steel frame. The exterior envelope includes large format glazing, roll-up industrial doors, louvers for mechanical ventilation, and embedded systems for future photovoltaic arrays. Internally, the facility is divided into multiple production zones, including body in white, paint, drive unit, battery cell, and final assembly areas. Each zone is outfitted with an integrated mechanical, electrical, and plumbing backbone tailored to the specific requirements of the manufacturing process. Electrical substations, bus ducts, and motor control centers distribute power to equipment, while compressed air, chilled water, and process piping systems run throughout the structure in overhead utility racks. HVAC systems consist of large rooftop air handling units with variable air volume controls and ductwork engineered for high-volume ventilation. Battery and paint shop areas are served by specialized air filtration systems and climate control to maintain environmental conditions necessary for quality control and safety. Fire protection includes wet pipe sprinkler systems, foam suppression in high-risk areas, and a network of fire alarm panels and detection devices distributed through ceiling and wall cavities. One of the most critical components of the expansion is the battery cell manufacturing area. This section requires ultra-clean environments, achieved through the use of clean room standards and enclosed spaces, positive pressurization, and air filtration. Mechanical isolation, anti-vibration pads, and precision leveling are incorporated into the floor systems to support sensitive equipment like electrode coating machines and cell assembly stations. Material movement throughout the Gigafactory is supported by automated guided vehicles, overhead cranes, and floor-mounted conveyors. These systems are designed to move components and finished products between zones without interfering with human workflow. Logistics tunnels, High bay racking systems and buffer storage areas are constructed to support just-in-time delivery and reduce operational bottlenecks. The facility's expansion also includes workforce amenities such as office space, cafeterias, training rooms, locker facilities, and employee parking. These support structures are built using conventional steel framing and modular interior finishes. Elevated walkways and observation decks allow management and visitors to safely monitor operations while minimizing interference with production. On the exterior, the expansion incorporates new access roads, loading docks, and utility corridors. Heavy-duty concrete pavements are laid for truck traffic and equipment transport, while perimeter fencing, lighting, and security systems are installed to maintain site safety. Landscape buffers and erosion control measures are implemented to minimize environmental impact and comply with regulatory requirements. The Gigafactory expansion is managed using advanced construction technologies, including building information modeling, 4D scheduling, and real-time project tracking. Construction crews work in multiple shifts to maintain continuous progress, with prefabrication and modular construction methods employed to accelerate timelines.
The Frederick Douglass Tunnel is a major infrastructure endeavor designed to replace the Civil War-era B and P Tunnel in Baltimore, Maryland, a critical bottleneck along the Northeast Corridor. The new tunnel will increase capacity, improve reliability, and allow for higher speed travel for both passenger and freight rail. It involves the construction of 2 new parallel rail tunnels, each approximately 2 miles long, designed for electric Amtrak and MARC trains, while also preparing the corridor for potential future upgrades. The construction process begins with preparatory work, including land acquisition, environmental remediation, and utility relocation. Due to the urban setting, crews must identify and divert existing sewer, water, and communication lines that intersect the future tunnel alignment. Extensive geotechnical investigations are carried out along the alignment, using boreholes and geophysical instruments to map subsurface conditions. These findings inform the selection of tunnel boring machine technology and the design of support systems for the tunnel lining. The primary construction method involves using large tunnel boring machines to excavate through a mix of soil and rock beneath West Baltimore. Launch shafts are constructed at staging areas, requiring deep excavations supported by secant pile walls or slurry wall systems to maintain soil stability. Once the shafts are completed, the tunnel boring machines are assembled in segments and lowered into place. As each machine advances, it excavates material which is conveyed back to the surface, while simultaneously installing precast concrete tunnel segments to form the permanent lining. Above-ground structures include a new West Baltimore station, portal structures at either end of the tunnel, and ventilation shafts spaced strategically along the alignment. Each tunnel bore includes track slab construction, overhead catenary systems for electric traction, signal conduits, emergency walkways, and fire life safety systems. These elements are built sequentially following tunnel excavation, requiring multiple specialized crews operating in coordination. To handle stormwater and groundwater intrusion, sump pits and drainage systems are integrated along the tunnel invert, with pumping stations to discharge water safely. Tunnel ventilation systems include jet fans and shafts to manage air quality and smoke extraction in emergency scenarios. Substations are constructed nearby to deliver traction power, linked by high-voltage feeders running through dedicated conduit banks. Once both tunnel bores are completed and internal systems installed, track is laid and aligned to tight tolerances to support high-speed rail operations. Extensive systems testing follows, including power supply validation, signaling integration, and emergency response simulations. Upon completion, the Frederick Douglass Tunnel will replace a nearly century-and-a-half-old choke point with modern, resilient infrastructure capable of supporting the Northeast Corridor's next generation of rail travel.